Thousands of gallons of raw honey are processed every day in high-speed factories that turn nature's purest ingredient into a global product. From massive filtration systems to automated bottling lines, this is honey production at a scale you've never witnessed before. Today we go inside the factory to uncover the incredible technology behind one of the world's most iconic natural foods. The industrial processing of honey begins not within the walls of the factory, but at the apiaries, where honeybees forage, collect nectar, and begin the complex enzymatic process of transforming floral sugars into the thick, golden liquid we know as honey. Factory-scale honey production starts with the careful coordination between contracted beekeepers and processing plants, which work together to supply bulk honey at a scale large enough to support mass distribution. The first step in the factory process involves the reception and inspection of raw honey as it arrives from the beekeepers' extraction sites. Raw honey is typically delivered in large food-grade steel drums or plastic totes, each capable of holding hundreds of pounds of honey. These containers arrive sealed, labeled with origin data, floral source if known, and batch tracking codes. Upon arrival at the honey processing facility, each container is unloaded onto the receiving dock, where a team of technicians begins the initial quality assurance process. This is far more than a visual check. Industrial honey processors must guarantee that the incoming product is pure, unadulterated, and meets strict legal and food safety standards. The drums are first sampled using a specialized honey sampling spear, a long stainless steel tube designed to pierce through the viscous mass and extract a vertical core from top to bottom. This is essential because honey can stratify with moisture content, color, and crystallization levels varying from top to bottom. The extracted sample is then homogenized and sent to the quality control laboratory. Here, a battery of tests is performed. Moisture content is measured using refractometers, which determine how much water is present in the honey. Legal standards require honey to contain no more than 20% moisture to prevent fermentation. Beyond moisture testing, analysts perform pollen analysis to verify floral sources and geographic origin, which is important for regulatory labeling and for upholding claims like clover honey or orange blossom honey. Additional tests, such as electrical conductivity, help differentiate between nectar and honeydew honeys, while HMF levels, or hydroxymethylfurfural, are checked to ensure the honey hasn't been exposed to excessive heat during prior storage or transit. High-performance liquid chromatography may also be used to detect the presence of added sugars, which would indicate adulteration and result in immediate rejection of the batch. Once a drum passes inspection and is approved for processing, it is moved to the uncrystallization station. Raw honey can crystallize over time, particularly when stored in cooler environments or when the floral source is rich in glucose. Crystallized or partially crystallized honey must be reliquefied before it can be filtered or blended. This is achieved by placing the drums in heated chambers or warm water baths, known as hot rooms, where they are gently warmed to temperatures around 95 to 110 degrees Fahrenheit. This temperature range is sufficient to melt crystals without degrading the honey's delicate aromatic and enzymatic properties. Large facilities often use drum heating tunnels that can accommodate dozens of drums at a time. These tunnels employ radiant heat panels and convection fans that maintain a steady, uniform temperature throughout the enclosure. Temperature probes are inserted into each drum to ensure that internal temperatures rise slowly and evenly, preventing localized overheating which could darken the honey or degrade its quality. This gentle warming process can take anywhere from 24 to 72 hours, depending on the degree of crystallization and the initial temperature of the honey when it arrived. Now it's time to go into the liquefaction and transfer stage, where the now softened honey is pumped out of the drums and into the factory's primary processing line. This step requires specialized food-grade pumps capable of handling thick, sticky materials without introducing air bubbles or damaging the honey's texture. Positive displacement pumps, such as rotary lobe or progressive cavity pumps, are commonly used for this purpose. These pumps are designed to move viscous fluids at a steady rate without causing foaming or aeration, which can negatively impact downstream processing. As the honey is pumped from each drum, it passes through heated stainless steel pipelines that maintain a consistent temperature, usually around 110 to 120 degrees Fahrenheit, to keep the honey fluid during transit. The pipelines are insulated to minimize heat loss, and the entire system is cleaned between batches using CIP or clean-in-place systems, which circulate hot water and food-safe cleaning agents to maintain sanitary conditions. Valves and flow meters are used to control how much honey enters the next phase, which is usually a settling or holding tank. These tanks are large vertical silos equipped with gentle agitation paddles to keep the honey uniform without whipping air into it. At this stage, the honey is allowed to rest briefly, giving suspended particles like wax fragments, bee parts, or pollen clumps time to rise or settle. Some facilities incorporate slow-flow decanting chambers or skimming belts that remove surface foam and floating debris. The goal here is to prepare the honey for the critical filtration stage without exposing it to excessive agitation or temperature shifts, which could compromise quality. But up next is the filtration stage, one of the most technically controlled steps in factory honey processing. The challenge with filtering honey lies in removing impurities while preserving beneficial properties such as flavor, aroma, and trace pollen content. To accomplish this, processors use a series of progressively finer filters, starting with coarse metal mesh screens and moving to finer, micron-level filtration pads or cartridges. Initially, the honey flows through vibratory sieve filters or centrifugal strainers that remove large debris, including chunks of wax or bee remnants. These are often equipped with auto-cleaning screens that rotate or vibrate to prevent clogging. After coarse filtering, the honey enters a fine filtration system. Depth filters composed of cellulose or food-grade polypropylene are commonly used. These filters remove particles as small as 5 to 10 microns, including residual wax, dust, and crystallized sugar particles that could initiate recrystallization in the final product. To aid this process, the honey is maintained at a precise temperature of about 120 to 130 degrees Fahrenheit, warm enough to reduce viscosity and improve flow through filters, but not so hot as to destroy heat-sensitive enzymes or antioxidants. Inline temperature sensors and automated control panels ensure that every gallon of honey is processed under identical thermal conditions. Some advanced facilities even use vacuum-assisted filtration to further reduce the need for high temperatures, thereby preserving more of the honey's raw characteristics. Once filtration is complete, the honey is collected in large stainless steel blending tanks. These tanks are used to homogenize different batches of honey, standardize flavor profiles, and adjust final parameters such as color and clarity. Mixing paddles rotate at slow, controlled speeds to avoid aeration while ensuring a uniform blend. It's at this stage that some producers may add trace amounts of previously tested and approved batches to maintain flavor consistency across large volumes, especially if multiple floral sources are involved. Now it's time to explore the homogenization process in more detail, as this step plays a pivotal role in ensuring that every bottle or jar of honey pulled from the line is virtually identical in texture, color, and taste. Honey, being a natural product, can vary widely between batches due to differences in nectar sources, collection times, and even seasonal variations. To manage these inconsistencies, processors rely on computer-controlled blending protocols that match incoming honey against established reference standards. Before blending begins, technicians perform sensory and analytical testing on the batch. including color measurement using the Fund scale, which classifies honey from water white to dark amber. Flavor notes are assessed by trained sensory panels or electronic nose devices, while moisture and acidity levels are verified to determine blending ratios. If a batch is slightly darker than the standard product line, a portion of lighter honey is added to balance the color. If a batch is too viscous, a blend with a slightly higher moisture content is introduced to bring the final viscosity within specification. Mixing tanks used in this process are often jacketed with warm water or glycol to maintain the blending temperature at a steady 110 to 120 degrees Fahrenheit. Internal baffles guide the flow of honey, ensuring thorough integration without the formation of dead zones or stratification. The tanks are usually equipped with inline sensors that continuously monitor parameters like Brix, viscosity, and turbidity. The blending cycle may take several hours for large volumes, and throughout the process, automated samplers pull small amounts at regular intervals to verify that the blend remains within quality parameters. Once homogenization is complete, the honey is transferred to the final holding tanks that feed directly into the packaging lines. These tanks are placed on load cells that precisely measure the volume of honey dispensed into each container. From this point forward, the product must move through sealed, temperature-controlled systems to ensure no contamination occurs before bottling. And that leads directly into the highly synchronized packaging phase. As the homogenized honey flows from the final holding tanks into the packaging system, the entire process becomes a high-speed, tightly orchestrated sequence of mechanical precision and hygiene control. This stage is where the product begins to take on its final consumer-facing form, whether it's packaged in squeeze bottles, glass jars, tubs, or bulk containers. The packaging line starts with the selection and preparation of containers, which are fed into the system from large hopper units or depalletizers, depending on the container type. Plastic bottles often arrive pre-formed and stacked in bulk, while glass jars may come in pallets wrapped in protective plastic film. Regardless of material, every container goes through a rigorous cleaning phase before it is allowed anywhere near the honey. The first step in container preparation is an air rinse or ionized air cleaning process. Each container is inverted and passed through a chamber where blasts of filtered, pressurized air are directed inside. Ionized air is used specifically to neutralize any static charges that might cause dust or particles to cling to the sides of the container. In glass packaging lines, this process may be supplemented with a vacuum extractor that removes dislodged particles immediately after the air rinse. Some facilities also opt for a UV light exposure chamber that the containers pass through as an added antimicrobial safeguard. All of these steps are executed on automated conveyor systems, synchronized to keep pace with the fill line. Now it's time to go into the filling stage, which must be executed with extreme accuracy to ensure every package contains the correct weight or volume of honey. Honey's thick, slow-moving consistency makes it a challenging product to fill efficiently at scale. To meet this challenge, factories use volumetric piston fillers or gear pump filling machines, both of which are well suited for handling viscous, sticky products. These machines are equipped with heated nozzles and jacketed tubing to maintain the honey at an optimal temperature, typically around 110 degrees Fahrenheit, so it flows smoothly without foaming or dribbling. Each filling station is designed with multiple nozzles, often ranging from 4 to 16, depending on the line's speed and scale. The nozzles are programmed to descend into the containers during filling and retract as the level rises, a method known as bottom-up filling. This minimizes splashing and helps prevent the introduction of air bubbles, which can interfere with the product's shelf stability and aesthetic appearance. Inline check weighers are stationed just downstream of the filling heads, automatically rejecting any underfilled or overfilled containers from the line. Any deviation outside a narrow tolerance window triggers an immediate alert and mechanical removal. Immediately after filling, the containers are transferred to the capping and sealing station. For plastic bottles, this often involves a torque-controlled capper that applies precise rotational force to ensure a tight but not damaging seal. Flip-top caps, disc-top caps, or screw caps are automatically sorted and fed into place using vibratory feeders and cap chutes. In the case of glass jars, the capping process may involve steam vacuum sealing with metal lids, creating a hermetic seal that ensures freshness and shelf stability. As the lid is applied, a puff of steam is injected into the headspace, which condenses and creates a partial vacuum as the jar cools. Some packaging lines also include an induction sealing station. This involves placing a foil liner inside the cap, which is then sealed to the lip of the container using electromagnetic induction to heat and bond the foil to the rim. This creates a tamper-evident barrier that reassures consumers while also acting as an additional contamination safeguard. Once sealed, the containers pass through a water or air rinse to remove any stray honey drips from the filling station, followed by a drying tunnel that uses forced warm air to eliminate surface moisture before labeling. But up next is the labeling and coding process, where the honey finally begins to take on its retail-ready appearance. Labeling machines apply product labels at high speed using pressure-sensitive or shrink-sleeve labels, depending on the packaging format. Pressure-sensitive labels are peeled from a backing roll and applied to the container with rollers, while shrink-sleeve labels are wrapped around the container and heat shrunk into place using a steam tunnel. Each label is applied with extreme precision using optical sensors that detect the exact placement zone, ensuring uniformity across all units. At this point, the line integrates the critical traceability step, date coding, and batch identification. Inkjet or laser coders are installed directly after the labeling station and are configured to print the production date, batch number, and expiration date onto the label, cap, or bottleneck. These codes are essential for tracking product back to its source in the event of a recall or quality issue, and they also help with inventory rotation throughout the supply chain. Vision systems verify the presence and legibility of these codes, and any container missing its code is automatically rejected from the line. Once labeled and coded, the honey containers move toward the secondary packaging phase. Here, they are grouped based on retail configuration, single bottles, multi-packs, or cartons, and loaded into larger corrugated cardboard cases. Robotic case packers or drop pack mechanisms handle this process with extreme care, particularly with glass containers, which require dividers and cushioning. Once the cases are assembled and filled, they're sealed using hot melt glue or tape and then passed through a check weigher to verify package weight consistency. The final stage in the packaging process is palletization, where filled cases are stacked in precise formations onto wooden or plastic pallets. Robotic palletizers equipped with vacuum grippers or mechanical arms lift and arrange the cases row by row, ensuring that weight is evenly distributed to prevent collapse during transport. Once the pallet is complete, it is wrapped with industrial stretch film to stabilize the load and protect it from moisture and dust. Each pallet receives a barcode label containing all relevant shipping and traceability data, including product type, quantity, destination, and handling instructions. Now it's time to go into the warehousing and distribution stage, which is vital to maintaining honey's shelf life and ensuring that product quality is preserved from the factory to the consumer. Honey is hygroscopic, meaning it absorbs moisture from the air, so warehousing conditions must be carefully controlled. Finished pallets are moved to temperature and humidity-controlled warehouse zones where the ambient environment is kept between 60 and 75 degrees Fahrenheit, with relative humidity below 60% to prevent moisture ingress that could lead to fermentation or spoilage. Inventory is managed using a warehouse management system that assigns each pallet a digital location code, tracks product age, and ensures first in, first out rotation. Automated guided vehicles or forklifts retrieve pallets based on shipping schedules, and every movement is recorded in a centralized database. This allows full traceability not just back to the packaging date, but all the way through blending batches and raw honey origins. If a quality issue were ever discovered post-shipment, the manufacturer could instantly identify and recall only the affected lot numbers. Before pallets leave the facility, they may undergo one final inspection. Logistics personnel verify that labels match the shipping documentation, confirm temperature logs for any time-sensitive products, and ensure that stretch wrapping and labeling meet the receiving distributor's requirements. Some retailers have specific palletization rules, like maximum stack height or barcode placement, that must be followed exactly to avoid supply chain disruptions. Once cleared, pallets are loaded into temperature-controlled trucks using dock levelers that ensure a smooth transition from warehouse to vehicle. These trucks are often equipped with sensors that track internal temperature and humidity levels during transit. If any threshold is breached during transportation, alerts are sent to the distribution center to allow preventive action. This step is critical because improper handling during shipping can undo months of careful processing. For instance, exposure to excessive heat can darken the honey, degrade its enzymes, and even trigger fermentation if the moisture content is borderline. As the honey moves through regional distribution centers and into retail outlets, it remains in sealed containers that shield it from light and air. Most honey has a shelf life of 2 years or more if stored properly, thanks to its low water activity and high sugar concentration, which naturally inhibit microbial growth. However, the quality and freshness perceived by the consumer are still closely tied to how well every part of the manufacturing and distribution process has been executed, from the bee to the bottle to the shelf. Every detail, every degree of heat, every micron of filtration, and every second of line timing plays a role in preserving the integrity of the final product. And even after it reaches store shelves, the story of how honey is made in a factory continues to resonate with precision, craftsmanship, and scientific control. To fully understand the industrial production of honey, it's important to go beyond the mechanics and explore the subtleties of product customization, regulatory compliance, and the final quality control processes that make factory-scale honey not just uniform, but legally marketable and consumer safe. After the honey has been packaged, palletized, and staged for distribution, another dimension of the process becomes active: the post-packaging quality assurance system. This system acts as a final safeguard to confirm that the product leaving the facility not only meets internal quality standards, but also complies with local, national, and international food safety laws. One of the most essential tasks during this final phase is the detailed sampling and archiving of batch samples. From each production lot, designated containers are pulled from the finished goods and sent to the factory's on-site analytical laboratory. These samples are catalogued, sealed, and retained in climate-controlled archives for up to several years, depending on regulatory requirements. This ensures that if a complaint, audit, or issue ever arises, the facility can test the retained sample and compare it to the current product in question. The archive system is tied directly into the facility's digital traceability records, allowing a sample to be matched instantly to the exact floral source. Filtration parameters, blend ratios, packaging date, and even which employee signed off on the batch. Parallel to this, comprehensive chemical and microbiological testing is performed on the pulled samples. Even though honey is naturally resistant to microbial growth due to its low water activity and high sugar content, every lot is still tested for yeast, mold, and spore-forming bacteria, such as Clostridium botulinum. The latter is especially critical for honey intended for infant consumption. Though honey is generally not recommended for children under 1 year of age, advanced polymerase chain reaction methods and microbial plating techniques are used in-house or sent to certified third-party labs for verification. The chemical testing regimen goes even deeper. In addition to previously mentioned standards such as moisture and HMF, tests are conducted to confirm that no contaminants have been introduced during packaging. This includes screenings for bisphenol A in plastic containers, phthalates, heavy metals like lead or arsenic, and residues from cleaning agents. Food-grade lubricants used in machinery are also tightly controlled to prevent incidental contact, and testing verifies their absence in finished products. Random bottles are sometimes subject to full shelf life simulation testing, where accelerated aging is used to project how the honey will behave under various conditions over time. Now it's time to go into the regulatory labeling and export compliance procedures, a crucial and often complex step for companies that ship honey across borders. Labeling is governed by a mixture of national food laws and international trade agreements. In the United States, for example, the Food and Drug Administration requires that honey be labeled with the common or usual name, net weight, ingredient list, the name and place of the business, and nutrition facts. Additional designations such as raw, organic, unfiltered, or wildflower must be substantiated with supply chain documentation and laboratory verification. For export to the European Union, labeling rules become even more intricate. The EU requires origin declarations if more than one country of origin is involved, meaning that a blend containing honey from, for example, Argentina and Canada must say, blend of honeys from more than one country, unless the exact percentages are broken down. Pollen analysis and isotopic testing are commonly used to verify the authenticity and origin of honey destined for the EU, and the entire production process must comply with the European Honey Directive. This includes ensuring that no heat treatment exceeds 40 degrees Celsius if the product is labeled as raw, and that no enzymatic activity is lost. The labeling department works in tandem with regulatory and export compliance officers, who maintain up-to-date databases of international standards, customs documentation, and product certifications. These certifications may include organic certificates, non-GMO verification, halal or kosher certification, fair trade documentation, and country-specific certifications of analysis. Every pallet destined for export is linked to a detailed manifest, and random audits ensure that the physical label matches its digital record in the product lifecycle database. Any discrepancy can halt a shipment and trigger a full traceability review. But up next is the specialization phase, where some facilities go beyond traditional honey and produce value-added variations to meet niche markets or changing consumer demands. This might include whipped or creamed honey, honey infused with natural flavors or botanical extracts, or honey blended with additives like royal jelly, bee pollen, or propolis. Each of these variations requires separate processing lines or batch scheduling to avoid cross-contamination and to comply with labeling laws that distinguish these products from standard filtered honey. Creamed honey, for example, requires controlled crystallization to achieve a smooth, spreadable texture. After filtration and homogenization, the honey is seeded with a small amount of finely crystallized honey and slowly stirred under cool temperatures in a creaming tank. This controlled environment allows microcrystals to form uniformly, resulting in a product that remains spreadable even when stored at room temperature. The tanks used in this process are jacketed with cooling fluid and fitted with slow-turning paddles that prevent the formation of large crystals. Flavored honey follows a different path. Natural flavor compounds, such as cinnamon, ginger, vanilla, lemon, or even chili are emulsified into a small portion of honey before being slowly blended into the main batch. This ensures even distribution and prevents hotspots of flavor. Each additive must be food safe, approved by regulatory bodies, and tested for interaction with honey's enzymes and acidity. In some cases, additional filtration or viscosity adjustment is needed to maintain the same flow behavior in the bottling equipment. These specialty honeys are typically packaged in smaller volumes and targeted toward gourmet or health-conscious consumers. PepsiCo takes extreme care in sourcing and treating water to ensure the final product is free from impurities, contaminants, and off flavors. Without this careful preparation, the beverage could have inconsistencies in taste, appearance, and carbonation retention. The journey starts with sourcing water from natural springs, municipal supplies, or underground wells, depending on the bottling plant's location. However, regardless of its origin, this water must go through extensive treatment to meet PepsiCo's strict quality standards. The process begins with initial screening, where water passes through coarse filters that remove large particles such as dirt, sand, and debris. This is followed by sedimentation, a method that allows heavier impurities to settle at the bottom while the cleaner water moves forward in the process. Once the larger impurities are removed, the next step is carbon filtration. This step is crucial for removing chlorine, organic compounds, and any unwanted odors or tastes that could interfere with the Pepsi formula. Activated carbon filters contain a highly porous material that traps chemical impurities while allowing pure water to flow through. This process not only improves the taste of the water, but also enhances its ability to mix well with the other ingredients later in production. But up next is the reverse osmosis process, one of the most advanced purification techniques used in beverage manufacturing. Reverse osmosis involves forcing water through an ultra-fine membrane under high pressure, effectively removing even the tiniest dissolved particles, including salts, minerals, and microscopic contaminants. This ensures that the water is as pure as possible before it becomes part of the Pepsi formula. To further refine the water, it undergoes ultraviolet sterilization. This step is essential for eliminating any remaining bacteria, viruses, or other microorganisms that could compromise the safety and shelf life of the beverage. High-intensity UV light disrupts the DNA of these microorganisms, rendering them inactive without the use of chemical disinfectants. Finally, before the purified water is stored, it goes through an ozonation process. Ozone, a highly reactive form of oxygen, is injected into the water to act as a natural sanitizer. This step ensures that the water remains free from microbial contamination while it is held in large stainless steel storage tanks, awaiting the next phase of production. Now that the water has been meticulously purified, it must be precisely balanced to create the ideal base for Pepsi. Even though reverse osmosis removes most dissolved solids, a controlled amount of specific minerals is added back into the water to optimize taste and improve its ability to retain carbonation. This step is carefully monitored as the mineral composition of the water can impact the final mouthfeel and texture of the beverage. With the water fully prepared and stored in sanitary tanks, it is now ready to be mixed with the other key ingredients that will give Pepsi its distinctive flavor. But before moving on to mixing, each batch of purified water is rigorously tested for quality. Samples are taken from the storage tanks and analyzed in PepsiCo's in-house laboratories. Scientists and quality control experts measure pH levels, mineral content, and overall purity, ensuring that each batch meets the company's global standards. If any irregularities are detected, the water is either reprocessed or discarded, preventing any inconsistencies from affecting the final product. Now that the water has been meticulously purified and stored in sanitized tanks, the next crucial step in the Pepsi manufacturing process is the preparation and addition of sweeteners. Sweeteners play a fundamental role in defining the flavor profile of Pepsi, contributing to its signature taste while also affecting mouthfeel, viscosity, and overall balance. The selection, processing, and precise blending of these sweeteners are critical to ensuring that every bottle and can of Pepsi maintains consistency across different production facilities worldwide. In most regions, Pepsi is sweetened with high fructose corn syrup, a liquid sweetener derived from cornstarch. However, in some markets, particularly in countries where cane sugar is more widely available or preferred, sucrose from sugarcane or sugar beets is used instead. Regardless of the source, the sweetener must be carefully refined and processed before being added to the beverage. The journey of high fructose corn syrup begins with corn milling, where harvested corn is cleaned, steeped, and ground into a slurry to separate the starch from the fiber, protein, and germ. The extracted starch is then subjected to enzymatic processing, where it is converted into glucose. A second enzyme is introduced to transform a portion of the glucose into fructose, increasing its sweetness. The result is a thick, viscous syrup that is then further refined, filtered, and tested to ensure the correct balance of glucose and fructose. The most commonly used variety in soft drinks is HFCS 55, which contains approximately 55% fructose and 45% glucose, closely mimicking the sweetness profile of cane sugar. For regions that use sucrose instead of HFCS, the sugar is derived from either sugarcane or sugar beets. Sugarcane is harvested, crushed to extract juice, and then boiled to concentrate the sugar, forming crystallized sucrose. Sugar beets, on the other hand, are sliced and soaked in hot water to extract sugar, which is then purified and crystallized. In both cases, the raw sugar undergoes extensive refining to remove impurities and ensure a uniform, pure sweetener. Once the sweetener is ready, it must be dissolved into a concentrated syrup before being mixed with other ingredients. In a dedicated mixing tank, the high fructose corn syrup, or dissolved sucrose, is blended with purified water in precise proportions to create a uniform sweetening solution. This syrup is continuously agitated to prevent crystallization and ensure a consistent texture. To maintain Pepsi's exact sweetness level, refractometers are used to measure the syrup's sugar concentration, ensuring it falls within the specified range. At this stage, the syrup is also subjected to rigorous quality control testing. Laboratory technicians take samples from each batch and analyze them for purity, consistency, and microbial safety. Any inconsistencies in sweetness or viscosity could alter the taste of the final product, so adjustments are made, if necessary, before moving on to the next step. Now that the sweetener has been perfectly prepared, it is time to introduce the key flavoring components that define Pepsi's distinctive taste. Pepsi's flavor is the result of a complex blend of natural and artificial flavorings, including citrus oils, spice extracts, and caramel notes. The exact recipe remains a closely guarded secret, known only to a select few within the company, but it is widely understood that ingredients like orange oil, lemon oil, vanilla, cinnamon, nutmeg, and cola nut extract contribute to the drink's signature profile. The flavoring components are carefully blended into a concentrated mixture known as the flavor base. This highly concentrated liquid is prepared in a separate, sterile mixing tank, where precise measurements of each ingredient are combined under controlled conditions. Some of these ingredients, particularly the essential oils, must be emulsified using stabilizers to ensure they mix properly with the water-based formula of Pepsi. Without proper emulsification, the oils could separate from the rest of the beverage, leading to inconsistent flavor distribution. Phosphoric acid is then added to the flavor base, providing Pepsi with its signature sharpness and tangy aftertaste. This acid also plays a crucial role in preserving the beverage by inhibiting microbial growth. The level of acidity is carefully controlled to balance the sweetness of the drink and enhance its overall flavor. Caramel color, which gives Pepsi its deep brown hue, is another essential ingredient added at this stage. This colorant is created by heating sugar compounds under controlled conditions, resulting in a stable and safe coloring agent. The intensity of the caramel color is strictly regulated to ensure that every bottle of Pepsi has the same visual appeal. Once the flavor base is complete, it must be thoroughly mixed with the sweetener solution to create the final syrup that will be used in the soft drink. This blending process takes place in large stainless steel tanks, where high-powered mixers ensure even distribution of all ingredients. The proportion of sweetener to flavor base is precisely measured, as even a slight deviation could alter the taste of the final product. Before the syrup is approved for use, samples are taken and analyzed in a quality control lab. Tests include pH measurement, viscosity checks, and sensory evaluations, where trained tasters confirm that the syrup matches Pepsi's standard flavor profile. These rigorous quality checks ensure that every batch of syrup is identical, maintaining Pepsi's global consistency. Once the syrup has passed all quality control tests, it is stored in temperature-controlled holding tanks, ready to be mixed with carbonated water. These tanks are kept under strict sanitary conditions to prevent contamination and preserve the integrity of the syrup. But up next is one of the most critical aspects of the Pepsi production process: carbonation. This step is responsible for the effervescence and refreshing sensation that consumers associate with soft drinks. Without proper carbonation, Pepsi would lose its signature fizz, altering the drinking experience. The process of infusing the beverage with carbon dioxide is both a science and an art, requiring precise control over temperature, pressure, and gas concentration. To begin the carbonation process, purified water is first chilled to near freezing temperatures. The reason for this is that carbon dioxide dissolves more efficiently in cold water than in warm water, ensuring maximum carbonation retention. The chilled water is then injected with high purity CO2 gas under controlled pressure, creating carbonated water. This water is then carefully blended with the pre-mixed syrup in an exact ratio, typically around 5 parts carbonated water to 1 part syrup. The precise proportion ensures the correct balance of flavor, sweetness, and fizziness in the final beverage. Maintaining the right level of carbonation is crucial, as it directly affects the mouthfeel and shelf life of the product. If the carbonation is too low, the drink will taste flat and less refreshing. If it is too high, the beverage may be overly acidic or cause excessive foaming during packaging. To ensure consistency, carbonation levels are continuously monitored using pressure sensors and dissolved CO2 analyzers. The newly carbonated Pepsi must now be handled carefully to prevent the loss of carbonation before packaging. At this stage, the beverage is kept under constant pressure in specialized holding tanks to maintain CO2 solubility. Any sudden release of pressure could cause the carbon dioxide to escape, resulting in a less fizzy drink. With the Pepsi now fully mixed, carbonated, and held under precise pressure conditions, the next step is bottling and packaging. This is one of the most intricate parts of the manufacturing process, requiring extreme precision, speed, and cleanliness to ensure that every bottle and can of Pepsi is filled, sealed, and prepared for distribution without losing carbonation or quality. The bottling process must take place in a sterile environment to prevent contamination, and the machinery involved operates at incredibly high speeds to keep up with global demand. The first part of this process involves the preparation of bottles and cans. Pepsi is available in a wide range of packaging formats, including glass bottles, aluminum cans, and plastic bottles made from polyethylene terephthalate. Each type of container has its own preparation requirements, but all must be thoroughly cleaned and sterilized before being filled. For plastic bottles, the process begins with small, preformed PET molds called preforms. These preforms are heated to a specific temperature and then rapidly inflated using high-pressure air inside a blow molding machine. This machine expands the preforms into their final bottle shape, ensuring uniform thickness and durability. The freshly molded bottles are then conveyed into a high-speed rinsing station, where they are thoroughly washed with filtered water and food-safe sanitizing agents to remove any potential contaminants. Glass bottles undergo a more rigorous cleaning process since they are often reused. They are first soaked in a high-temperature caustic solution to break down any residue from previous use, followed by multiple rinses with clean, filtered water. Finally, they pass through a steam sterilization chamber to ensure that no microorganisms remain. Aluminum cans, on the other hand, arrive at the bottling plant pre-formed and ready to be filled. However, before filling, they are sent through a high-pressure air jet cleaning system that blasts away dust and debris. Since aluminum cans are highly sensitive to corrosion, a thin food-safe lining is applied inside each can to prevent any reaction between the beverage and the metal. Now that the bottles and cans are fully prepared, the filling process can begin. The carbonated Pepsi is transported through a network of pressurized stainless steel pipes that maintain the beverage's optimal CO2 concentration and temperature. The filling machines operate at high speeds, capable of processing thousands of containers per minute. For PET and glass bottles, filling is done using gravity-based or counter-pressure filling systems. In a counter-pressure system, the bottle is first pressurized with CO2 before the Pepsi is introduced. This prevents foaming and excessive carbonation loss during filling. The precise amount of liquid is dispensed into each bottle, with sensors ensuring that no underfilled or overfilled bottles proceed down the production line. Aluminum cans require a slightly different approach. Since they are more prone to CO2 loss due to their wide openings, the filling nozzles are designed to minimize turbulence as the liquid enters. The cans are quickly filled and then topped with a small injection of nitrogen gas to prevent oxidation before being sealed. Now that the containers are filled with carbonated Pepsi, the next critical step is sealing. This process must be done immediately after filling to prevent carbonation loss and contamination. For plastic and glass bottles, this involves capping. Screw-on plastic caps are applied to PET bottles using high-speed rotary capping machines, which tighten each cap with precise torque to ensure a secure seal. Glass bottles, often used for premium or international markets, are sealed with either metal crown caps or twist-off caps, depending on the region. Aluminum cans are sealed using a double seaming process. A lid, which contains an integrated pull tab, is placed on top of the can and then mechanically crimped around the rim. This creates an airtight seal that locks in carbonation and prevents leakage. With all the containers now sealed, they move on to the quality control phase. At this stage, random samples are pulled from the production line and tested for multiple factors, including fill level, carbonation retention, pressure stability, and contamination. Advanced X-ray and laser scanning systems inspect each bottle and can to ensure that there are no foreign particles, dents, or defects in the packaging. Any defective units are immediately rejected and removed from the batch. Once the beverages pass quality control, the containers proceed to labeling. Each bottle and can receives a label that includes branding, nutritional information, ingredient lists, and regulatory compliance markings. PET bottles have labels applied using heat shrink or pressure-sensitive label machines, while aluminum cans typically have their designs pre-printed onto the metal surface. After labeling, the bottles and cans are grouped into multi-packs for retail distribution. This process involves bundling them into various configurations, such as 6-packs, 12-packs, or full cases. Plastic shrink wrap, cardboard trays, or molded carrying handles are used to secure the multi-packs for easy transportation. The completed packs are then stacked onto pallets in an organized manner and wrapped in stretch film to stabilize them for shipping. Now it's time for one of the most logistically challenging aspects of Pepsi production: distribution. The pallets of finished Pepsi products are moved to temperature-controlled warehouses where they are stored before being shipped to retailers, grocery stores, vending machines, and restaurants. Since Pepsi is produced in enormous quantities to meet global demand, distribution logistics must be precisely managed to ensure that every store and vendor receives fresh products. Pepsi's supply chain is a highly coordinated operation involving fleet management, refrigerated storage, and just-in-time delivery systems. Large distribution centers act as hubs where shipments are sorted based on region and customer demand. Trucks, rail transport, and even cargo ships are used to move massive volumes of Pepsi across countries and continents. Once the products arrive at their final destinations, they are placed in cold storage or directly onto store shelves. In grocery stores and supermarkets, Pepsi is often stored in temperature-controlled sections to maintain freshness. Restaurants and fast food chains receive large volumes of Pepsi in bulk containers, which are connected to soda fountains for on-demand dispensing. Throughout this entire process, PepsiCo maintains strict inventory tracking and quality assurance programs. Each batch of Pepsi is assigned a unique tracking code, allowing the company to trace products back to their production date, location, and ingredient sources. This ensures that in the event of a recall or quality issue, affected products can be quickly identified and removed from circulation. With the Pepsi bottles and cans now filled, sealed, labeled, and packed for distribution, one of the final but most crucial aspects of the manufacturing process is ensuring product consistency, longevity, and consumer satisfaction. Maintaining Pepsi's signature taste and quality across millions of bottles and cans requires an advanced system of quality control, storage optimization, and packaging innovation. Every aspect, from the shelf life of the product to the materials used in packaging, plays a role in ensuring that each Pepsi delivered to a consumer is as fresh and enjoyable as the last. The first key factor in Pepsi's shelf life and consistency is its ability to retain carbonation over time. Carbonation, which gives Pepsi its signature fizziness, is created by dissolving carbon dioxide into the liquid under high pressure. The challenge is ensuring that this CO2 remains trapped within the beverage from the moment it is bottled until it is opened by the consumer. To maintain carbonation, Pepsi uses specially designed bottles and cans that act as airtight barriers, preventing CO2 from escaping. Plastic bottles made from polyethylene terephthalate are engineered with multiple layers that slow down gas diffusion, preventing CO2 from seeping out over time. The thickness and structure of PET bottles are carefully optimized to balance durability with weight, ensuring that the bottles are strong enough to retain carbonation while remaining lightweight for transportation. Aluminum cans provide an even better barrier against gas loss. Their completely sealed structure ensures that no CO2 escapes, preserving the drink's fizziness for extended periods. Additionally, a protective food-grade lining inside each can prevent any reaction between the metal and the beverage, which could otherwise affect flavor. Glass bottles, often used for premium markets or limited edition versions of Pepsi, offer the best gas retention of all packaging types. Glass is completely impermeable, meaning that Pepsi stored in glass bottles maintains its carbonation for the longest period. However, glass is heavier and more fragile than plastic or aluminum, making it less practical for mass production and distribution. Another critical factor in product longevity is preventing oxidation. Exposure to oxygen can alter the taste of Pepsi, causing it to become flat and develop off flavors over time. To counter this, PepsiCo employs nitrogen dosing in certain packaging lines. This process involves injecting a small amount of nitrogen gas into PET bottles just before sealing. The nitrogen displaces any residual oxygen inside the bottle, reducing the risk of oxidation while also adding structural rigidity to the bottle, preventing it from collapsing under vacuum pressure. Beyond carbonation and oxidation control, preservatives also play a role in maintaining Pepsi's freshness. While the beverage's acidity and carbonation naturally inhibit microbial growth, additional preservatives such as sodium benzoate are included to extend shelf life further. These preservatives prevent mold, yeast, and bacterial growth, ensuring that Pepsi remains safe for consumption for months or even years after production. Now that the beverage's stability is secured, it must be stored and transported under optimal conditions. Pepsi is highly sensitive to temperature fluctuations, which can affect carbonation retention and overall flavor. As a result, warehouses, distribution centers, and retail storage areas are kept within a controlled temperature range to prevent heat exposure. Excessive heat can accelerate CO2 loss in plastic bottles and increase oxidation reactions, leading to a flatter, less refreshing drink. To counteract this, refrigerated warehouses are used in regions where high temperatures could compromise product quality. During transportation, trucks equipped with climate control ensure that Pepsi is not exposed to extreme heat or direct sunlight, both of which could degrade the beverage. Another major factor that affects Pepsi's taste consistency is the impact of light exposure. Ultraviolet light can break down some of the organic compounds in Pepsi's flavoring, leading to unwanted taste changes. This is why Pepsi bottles, particularly those made from PET, are designed with tinted or opaque plastic to reduce UV penetration. Aluminum cans and glass bottles naturally provide complete light protection, further ensuring product stability. Once Pepsi reaches its final retail destinations, whether in grocery stores, vending machines, or fast food chains, it is crucial that storage guidelines continue to be followed. Retailers are instructed to keep Pepsi stock rotated, ensuring that older products are sold first and newer shipments are stored properly. This helps maintain product freshness for consumers while preventing expired stock from sitting on shelves. Fast food chains and restaurants that serve Pepsi from soda fountains have additional steps to ensure taste consistency. Instead of pre-packaged bottles and cans, Pepsi is delivered to these locations in large pressurized syrup containers known as bag-in-box systems. These containers hold concentrated Pepsi syrup, which is mixed with carbonated water on demand through specialized dispensing machines. The bag-in-box system allows for efficient storage and prevents waste, as restaurants can control the syrup-to-water ratio for optimal taste. These systems are regularly maintained, with filters and carbonation settings adjusted to match the ideal flavor profile. Additionally, PepsiCo provides restaurants with quality control tools to measure CO2 levels and syrup concentration, ensuring that every poured glass tastes as good as a bottled Pepsi. With all these measures in place, Pepsi is now fully ready for consumers to enjoy. But beyond the immediate production and distribution, PepsiCo continually invests in research and development to improve manufacturing efficiency, sustainability, and packaging innovations. One of the company's most significant focuses in recent years has been reducing the environmental impact of its packaging. PepsiCo has made major advancements in recyclable PET bottle technology, developing bottles that contain post-consumer recycled plastic to cut down on waste. Additionally, the company has experimented with plant-based PET alternatives that reduce reliance on petroleum-based plastics. Aluminum cans have also been a major target for sustainability improvements. Since aluminum is highly recyclable, PepsiCo has worked to increase the amount of recycled aluminum used in can production. The company encourages consumers to participate in recycling programs, ensuring that cans are properly collected and reused. In some markets, PepsiCo has even introduced refillable glass bottle programs, allowing consumers to return used bottles for sanitation and reuse, significantly cutting down on single-use waste. Further technological advancements in bottling machinery have also improved efficiency in the production process. Firstly, that beast machine steps into the fields and starts shaking, loosening the peanuts from the roots and turning them inside out. After the plants are dug up, they're left to dry in the sun for a few days. Now the excess moisture is removed from the peanuts, and they are ready to be picked up. Here come those bulky mechanical friends to do this job. Way much easier than it seems. It picks up the dried plants, separates the peanuts from other debris, and collects them in a hopper. From the last decade, China has been the largest producer of peanuts, and this strategic country usually makes a final count of around 20 million tons of peanuts every year. We have arrived at the facility where the entire peanut pile is fed into the cleaning setup. The unwanted stuff, like stones, twigs, and other foreign materials, is removed through pre-screening. This deshelling process is most satisfying when the machines delicately remove the outer shells of peanuts and reveal that beautiful, potential, and healthy nut we all were waiting for. Hang in there for a moment. They need to inspect manually for a quality check before they send the peanuts towards seed coating removing machines. Here, with gentle shaking, a lot of air pressure, and proper programming, that brownish skin is removed from the peanuts. The peanuts are treated with a medium boiling process to lock their texture and flavor and sanitize them by killing off any harmful bacteria or microorganisms by keeping the approximate boiling temperature near 121 stacking Celsius. However, it varies from company to company. As soon as the hopper is filled with the boiled peanuts, they are immediately packed and sealed in cans for distribution. These roasted peanuts are going to transform into something super buttery and delicious. Following a little roasting, the peanuts are cooled down to reach a temperature that is safe for handling and prevents them from becoming too hot or soggy during grinding. Those chosen peanuts take a trip towards this grinder and start revealing the smooth, buttery paste we all crave. It keeps grinding the peanuts until it reaches the desired smoothness, and the magic ingredients that will enhance the flavor keep being added little by little. This whirlwind of crushing and blending turns those nuts into pure deliciousness until it's homogenization. This step is chaos that gives way to harmony. Through higher pressure, the peanut butter gains its final and smooth texture. Witness this final stage where the bottles are getting filled and sealed to secure the fresh peanut butter inside. Automated machines, like filling and cap sealing machines, work tirelessly, ensuring each jar is brimming with creamy goodness. Each jar gets dressed up, ready to impress on the supermarket shelf. Whether spread on toast, topped over ice cream, or simply enjoyed with a spoonful, chocolate peanut butter never fails to delight the senses. Chocolate peanut butter serves the taste buds with its rich, creamy texture and harmonious blend of sweet and nutty flavors. Look at those different patterns those machines are creating to give us that satisfying sight. It's more like a powerhouse of protein and other essentials for muscle repair and growth. It's delicious and satisfies your hunger between meals. Those roasted peanuts are ready for a delicious chocolate coating. This chocolate coating process requires precision to ensure each peanut is evenly coated. After coating, the peanuts are left to cool and harden. Once cooled, they are carefully packaged into food-grade safe containers for distribution and sale. Have you ever tried these? Honestly, I never have. If we talk about those chilled, delightful ice creams, you all know it's pretty popular around the globe. Every day in the United States, people consume around 50 million ice cream pints. That's enough to fill more than 9 Olympic-sized swimming pools. Whether it's a hot summer day or a chilly winter evening, Americans' love for this sweet treat stays strong all year round. And why wouldn't it? Just look at how creamy, rich, and delightful they are. Have you ever tried these Taiwanese crackers? They are pretty familiar and loved by many, from adults to children. In addition to their delicious taste and texture, Taiwanese crackers are also celebrated for their simplicity. Made from basic ingredients, they create a magical burst of flavors inside your mouth. Their straightforward approach allows the natural flavors to shine through, resulting in an authentic and satisfying snacking experience. These snacks come in a range of textures, from crispy and airy to dense and crunchy. In the last few years, there have been several conspiracies about their oil spraying, but I don't think it is a problem. Because if you dig deeper, snacking as a whole would be considered unhealthy. But after much time, a little snacking won't hurt. Do you agree? No doubt at least their production is pretty satisfying to watch. Check out the magical power of these automated systems for juice-filling sectors, where every drop counts, reducing electricity consumption. You will barely see more than a few workers working around because of the efficient automation. Talking about these bulky productions is my love language. I always fall for them. Do you? If it's a yes, we are the same, bro. So cheers to that. I want you to comment down below and let us all know whether you prefer bottled or fresh juices and why that is. Think you had a hard time scooping out the sweet and juicy flesh from the pineapple shell? I ruined 4 large pineapples just to bring out a nice pineapple ring. Didn't waste the rest though. Surprisingly, burger meat patties are low in carbs. A beef patty typically has none unless extras are added. These delicious burger patties are full of energy and nutrients, perfect for fueling your day in the most appealing ways you have ever imagined. Dried apricots are far healthier, sweet-dried fruits that can be enjoyed on their own as a satisfying snack or added to various dishes like salads, oatmeal, trail mix, or baked goods for a natural sweetness and nutritional boost. However, it's important to consume dried apricots in moderation due to their concentrated sugar content. Strawberries are delicious, sweet, and one of the most consumed fruits worldwide. But the question is, how can we have them fresh throughout the year? It has become more convenient since companies launched canned foods. This way, we can enjoy fresh strawberries all year round, even when they are not in season. Popping open a can and getting a burst of summer in every bite, either to top on your morning yogurt or blend into a smoothie, these beautiful fruits give you a lovely vibe. Honestly, these chickens are far more taken care of here, secure and cleaned, than in other local farms. Even in those large poultry facilities, they keep an eye on every chicken using robotic scanners, so they know every chicken is healthy, happy, and playing in advanced barns. Plus, did you notice those eggs systematically laying on the front row? That's how their automation works. It's all being observed and monitored until the eggs safely reach these units, where they will be tested for quality, etc. Here, the eggs automatically arrange for several inspections, like leak detection and cleaning purposes. Now comes this major egg inspector, which will approve only good eggs before they go into the disinfection chamber to remove any microorganisms or pathogens. And lastly, they are ready to come your way. No matter how some people oppose the idea of bottled juices, soft drinks, or any other processed liquids having a limited time at breakfast, I fall for those bottled and tasty juices every time. We all know it's not a healthy activity. I mean, it hardly takes 10 to 15 minutes to extract fresh juice. Anyway, that's not just my problem. The majority of us choose convenience. I'm glad we made it out successfully. Most importantly, together. And please take good care of yourselves. You are precious. If we need to make that yummiest jam, we probably should focus on the healthy growth of the fruits too. Now this matter is being set under a strict guide. But yeah, giving those pots the healthier and fluffy mud with the precise amount of materials. Now these robots start at the bottom by planting strawberry plants in containers or pouches. Water is essential, so they water each pot carefully to keep the strawberries happy and hydrated. When the strawberries grow big and red, it's time to pick them. For this purpose, this gigantic robot activates its clutches to delicately pick the ripened strawberries only. Since they're on different levels, it's easy to reach and pluck the delicious berries. This entire automation is so beautiful and satisfying. How these robots peculiarly pick up the strawberry from the stem and cut it without harming it. In botanical terms, berries have their seeds inside the flesh, but strawberry seeds are on the outside, so they didn't consider it in the berry list. Those fresh strawberries have arrived at their final destination, and here they will get even royal treatment. Just a little stop for a weight check. Once they make sure the demanded number of strawberries has arrived, they take them to the sorting units. And you better know what's going to be here with them. Of course, keeping you in mind, they're going to take that stack of strawberries for a manual check and make sure that only good quality strawberries are going further. Once they're sure of that, they let them pass on until they reach safe hands. Yep, these people are going to place each strawberry in that mold for the game-changing results. These robots automatically detect the green hull of a strawberry and beautifully just remove it without harming any other inch of the fruit. This is mind-blowing. Everything is under mechanical control. You can see how sharp eyes they have. Come on, they're doing this for you. Strawberries grow close to the ground, making them more susceptible to dirt, sand, and even tiny insects. The first wash, often a combination of water and little vibrations, removes these surface impurities. That's very important. But you know, fruits and veggies like these need another bath too. That's why they're given a second wash, often involving specialized sprays or misting with solutions like chlorine dioxide, which takes care of the tougher particles like pesticide residues and bacteria. This double trouble approach ensures the strawberries are as clean and safe as possible. They care about you. We care about you. See how honored we are to have you, just like these red, juicy strawberries. These fresh strawberries are now put into these containers. Yep, that's how you get the true and fresh flavor of frozen strawberries, because they are the same as, what to say, straight from farms to your plate. They are packed and firmly sealed to lock the pulpy fruit inside the food-grade containers. Just check out that large number of cans. Secondly, they use some of the frozen strawberries to make that glittery, yummy strawberry jam. All these frozen berries are put into the carriers to take them to the next stop, which is to load them into a container to add further ingredients. As the strawberries are loaded, now it's time to add further ingredients like sugar. They make sure the jam looks good, tastes good, and has the perfect texture. Once the handsome amount of sugar is poured, they need to control those figures and machines' capabilities by playing with some important buttons. The hot water tub is ready for these beautiful entities to enter and get bathed in the sweet syrup. What are they peeking at? Okay, the real drama has just begun. Once all the pulp comes to mix in that syrup, they put that material through sieves. This is important to give you that pulpless, smooth, jiggly jelly jam. Mixing, and more mixing. Everything is heated up in big pots or machines to make the strawberries blend and taste awesome. A special thing called pectin is added to make the jam just the right thickness. It's time to cook the material until it reaches its perfect texture, and that desired texture can be seen here. I think it's done. Yep, he's going to test the jam base to see if it's ready or needs to be cooked more. And yeah, it's good to go. Now the final process begins, to churn the mixture, to add a little more smoothness and to cool it side by side. A little now, it's like letting the flavors and texture settle and become best friends before they get packed into jars. And just wait, here we go. The whole warm jam base is ready. More close up here. It is, that creamy, smooth flow of my favorite jam. It's driving me crazy. Okay, time to pour that base and lock it in the jars. For that, these empty and starving bottles arrive. They are first neatly organized properly. The jam is carefully poured into jars all by itself. This process is usually automated in factories, with machines making sure each jar gets the right amount of fruity goodness. Here, we reach their sealing stage, where lots of lids are first picked in a proper style, beautifully conveyed to the roller coaster sort of belt, and finally to the sealing section where machines tightly seal the jars with lids. Okay, all those bottles are washed after being tightly sealed so that whatever sweetness remains on the outer side of the jars will be bathed away. We're now in the sticker section, where the robots will conveniently wrap stickers around these bottles so you will easily identify it's factory sealed. And of course, read that chart before eating anything. It's a good habit though. If you do, well, I don't. There's another technique too to add the labels one by one. All the bottles are labeled from whatever company they belong to and then piled up in the containers for the final bulk packaging. Bye-bye jam bottles. Don't forget my address and reach me soon. These mini jam bottles are filled up with the same freshness of fruit pulp and flavor to enrich your taste buds. Are those little nasty jam packets? You know, the ones at restaurants tucked next to the bread basket, bursting with fruity sunshine in one tiny bite. They're more than just sugar bombs. They might be tiny, but they're full of flavors to serve as starters for every meal. Also, these bite-sized marbles help stop food waste and make sure every spoonful is just right. These machines are the backbone of many industries, from food production to textile manufacturing to construction. With their robust blades and precise cutting mechanisms, they're built to tackle even the toughest materials. Imagine a scene where smoky aromas fill the air as meat sizzles on the grill, tantalizing taste buds with every flip and sear. Curious about the staggering output of flatbread producing machines in a single day? Prepare to be amazed. These efficient marvels can churn out an impressive number of flatbreads thanks to their high-speed capabilities and precision engineering. Depending on the size and capacity of the machine, production numbers can vary widely, ranging from thousands to even tens of thousands of flatbreads per day. Crafted with the finest ingredients and expert techniques, our pastries are a symphony of flavors and textures. Meet chocolate depositors, the sweet secret behind every delectable treat. Hazelnuts are packed with nutrients like protein, healthy fats, fiber, and various vitamins and minerals. Not only do they promote heart health and aid in weight management, but they also support brain function and contribute to healthy skin and hair. These little blue gems are packed with antioxidants, which help fight off harmful molecules in our bodies and keep us feeling great. motivate us to create more satisfying videos like these, and smash the like button. These factories aren't just about quantity, they're about crafting quality too, ensuring that each slice of salami delivers a burst of savory perfection. Removing the skin helps trim down on excess fat and calories. You see, much of the fat in chicken resides in the skin. So by peeling it off, you're opting for a leaner, healthier option. Additionally, without the skin acting as a barrier, marinades and seasonings can penetrate the meat more effectively, enhancing flavor throughout. Talking about almonds, you must eat them daily so you can remember us and keep watching our videos. Cheese holds a special place on plates globally, with millions indulging in its creamy goodness daily. Hey, if you're enjoying this video, make sure you hit that like button so we'll know how many people are interested in watching our upcoming videos. The ancient Egyptians were one of the first civilizations to enjoy sweets, using honey as a primary sweetener. That minced meat, also known as ground meat, is incredibly versatile and used in a wide array of dishes worldwide. From savory meatballs to juicy burgers, its adaptability knows no bounds. It all boils down to freshness and food safety. Ideally, you want to consume tray-sealed meat within a few days of purchase to ensure peak freshness and flavor. Let's crunch into the world of factory-made delicious potato chips. From sourcing the finest potatoes to adhering to strict quality control standards, these factories ensure that each chip meets the crispy, satisfying standard you expect. These machines are the backbone of large-scale food operations, capable of handling a wide variety of produce with speed and accuracy. These factory-prepared meals undergo stringent quality control measures to ensure they meet safety and nutritional standards. From automated sorting systems that ensure only the highest quality ingredients make it onto the production line to state-of-the-art packaging machines that swiftly seal products for freshness, these machines are essential for meeting consumer demand while maintaining high standards. Each pepper is carefully inspected for size, color, and quality, ensuring only the best make it to market. Each juicy bite is a refreshing explosion of tangy sweet goodness, leaving taste buds dancing with delight. These innovative contraptions are designed to streamline the process of pouring batter with precision and consistency. These machines are the masters of precision, effortlessly dispensing just the right amount of batter, dough, or filling with each press of a button. That's where the multi-head weighing machine shines. Its multiple weigh heads work simultaneously to ensure accuracy and efficiency. Imagine effortlessly removing the outer layer of fruits and vegetables with precision and finesse. That's the magic of these machines. From potatoes to oranges, they strip away the tedious task of manual peeling, saving you time and labor costs. But it's not just about convenience, it's about consistency. With peeling machines, you get uniform results every time, ensuring your products look as good as they taste. Wait. Before watching this clip, were you thinking peeling fruit is the hardest thing to do? I mean, it's messy, but not anymore. It's not just about indulgence, there are benefits too. Chocolate breads pack a double punch of flavor and nutrition. Bursting with tropical flavor and juiciness, mangoes are nature's candy that never disappoints. From automated temperature control to efficient oil filtration systems, they're designed to optimize performance and minimize waste. Flour is the primary component, usually made from wheat, and it is carefully milled to achieve the right texture and protein content for cake production. Sugar is another crucial ingredient, providing sweetness and structure to the cake batter. Granulated sugar, powdered sugar, and sometimes liquid glucose are used depending on the specific type of cake being manufactured. Eggs, either fresh or in liquid or powdered form, contribute to the structure and moisture of the cake. Dairy ingredients such as butter, milk, and cream enhance the flavor and texture. Vegetable oils, often used as a substitute for butter in large-scale production, ensure a longer shelf life and a softer crumb. Leavening agents such as baking powder or baking soda are essential to create the airy texture that defines a good cake. Flavoring agents including vanilla extract, cocoa powder, fruit purees, and artificial flavors are precisely measured and incorporated to achieve consistent taste profiles. Before production begins, the factory undergoes rigorous sanitation procedures to ensure a clean environment. Production lines, mixers, conveyors, and baking equipment are all sterilized to prevent contamination. The ingredients are stored in temperature-controlled silos or containers, with automated systems regulating their dispensation. Large-scale cake production begins with precise ingredient measurement. Factories utilize automated weighing systems that ensure every batch maintains the correct proportions. Dry ingredients like flour, sugar, and leavening agents are sifted and aerated to remove clumps before entering the mixing phase. Liquid ingredients such as eggs, milk, and oils are stored in large tanks and piped directly into the mixing units. Mixing is a critical step in cake production, requiring advanced industrial mixers that can handle large volumes while maintaining consistency. The process varies depending on the type of cake being produced. Sponge cakes require aeration to create a light texture, while denser cakes need thorough mixing to ensure a uniform crumb. Continuous batter mixing systems operate at high speeds, gradually incorporating the ingredients in precise sequences. Some factories use planetary mixers, which rotate on multiple axes to create an even distribution of ingredients. Ribbon blenders or high shear mixers may also be used to emulsify fat-based batters. Mixing times and speeds are carefully programmed to avoid overmixing, which can result in tough cakes. Once the batter reaches the desired consistency, it is transferred through a network of pipes or conveyor belts to the depositing machines. These machines portion the batter into molds, trays, or baking pans, ensuring uniformity in weight and shape. Modern cake factories employ volumetric or piston-based depositors that release precise amounts of batter with each cycle. Some machines are equipped with multiple nozzles to fill several trays simultaneously, increasing efficiency. At this stage, Additional ingredients such as fruit pieces, nuts, or chocolate chips may be incorporated, either mixed into the batter or sprinkled on top before baking. The filled molds or trays move along a conveyor system into industrial ovens. The baking process is meticulously controlled to achieve the desired texture and color. Tunnel ovens, rack ovens, and convection ovens are commonly used in large-scale cake production. Tunnel ovens, which feature continuous conveyor belts that move cakes through different temperature zones, ensure even baking. The temperature and humidity levels within the ovens are carefully regulated to promote consistent rising and moisture retention. During baking, leavening agents react with heat to create gas bubbles, causing the batter to expand. The Maillard reaction, a chemical process between amino acids and sugars, develops the golden brown crust and enhances flavor. After baking, the cakes must be cooled to prevent condensation and sogginess. Cooling tunnels equipped with controlled airflow rapidly bring down the temperature while preventing excessive moisture loss. The cooling process is crucial because cakes that are too warm can compromise the integrity of icing or packaging. Factories often employ spiral cooling conveyors that maximize space efficiency while allowing cakes to cool gradually. Some facilities use blast coolers that rapidly reduce temperatures without affecting texture. Once sufficiently cooled, cakes may be removed from their molds using automated depanning systems. These machines use gentle vibrations, air pressure, or mechanical arms to lift cakes without damaging their shape. Before proceeding to decoration, quality control checks are performed. Cakes are inspected for uniformity in size, shape, and color. Advanced vision inspection systems use cameras and sensors to detect defects such as uneven surfaces or air pockets. Weight sensors ensure each cake meets the required specifications. Any cakes that do not pass quality checks are either reworked or discarded. Some factories employ metal detectors and X-ray scanners to identify foreign objects or contaminants. The decoration process varies depending on the type of cake being produced. For layer cakes, automated slicing machines cut the cakes horizontally to create multiple layers. These layers are then conveyed to filling stations, where robotic arms or extrusion nozzles apply cream, fruit preserves, or ganache. In some cases, conveyor systems transport the cakes through enrobing machines, which coat them in a layer of chocolate or glaze. Icing and frosting are applied using precision nozzles, spatula robots, or rotary icing machines. Buttercream, fondant, or whipped cream is spread evenly across the surface. Some factories use airbrush systems to add gradients of color or decorative effects. For cakes that require intricate designs, programmable robotic arms pipe decorative elements with incredible precision. Sprinkles, chocolate shavings, or edible glitter may be added using automated dispensers. At this stage, cakes intended for retail packaging may be pre-sliced using ultrasonic cutting machines. These machines utilize high-frequency vibrations to create clean, precise cuts without crushing the delicate cake structure. Pre-sliced cakes are often packaged in individual portions for convenience. Cakes intended for long shelf life may undergo additional processes such as modified atmosphere packaging, which removes oxygen from the packaging to slow down spoilage. Packaging is a crucial step in maintaining product freshness and ensuring a visually appealing presentation. Cakes are carefully transferred onto packaging conveyors, where they are placed into plastic trays, paperboard cartons, or clamshell containers. Flow wrapping machines seal individual cakes in airtight film to extend shelf life. For larger cakes, shrink wrapping or rigid plastic domes provide protection during transportation. Labels with product information, barcodes, and expiration dates are applied using automated labeling machines. Before distribution, final quality control checks are performed. Cakes are weighed again to confirm portion accuracy. Some factories conduct random sampling to test for taste, texture, and moisture content. Microbiological testing may be carried out in on-site laboratories to ensure food safety compliance. Cakes are then organized into cartons or crates and palletized for transportation. Temperature-controlled storage areas maintain product freshness before shipment. Depending on distribution requirements, cakes may be transported in refrigerated trucks to prevent spoilage. Large-scale manufacturers distribute cakes to supermarkets, bakeries, and retailers across vast geographical areas. Once the cakes are packed and ready for distribution, they move through a final inspection stage to ensure that packaging integrity is maintained. Automated vision inspection systems scan the packaging for any defects, such as improper sealing, misaligned labels, or damage that could compromise product quality. Any faulty packages are removed from the production line to prevent them from reaching consumers. At this stage, lot numbers and expiration dates are printed onto the packaging using high-speed inkjet printers or laser etching machines, allowing for precise tracking and traceability. This is a critical aspect of food safety regulations, as it enables quick recalls in the unlikely event of contamination or quality issues. Once the cakes have passed all final quality control checks, they are transported to cold storage or distribution centers. Cakes that require refrigeration, such as those with fresh cream or perishable fillings, are stored in temperature-controlled environments to maintain freshness. These storage areas are monitored by advanced refrigeration systems that maintain optimal humidity and temperature levels. Cakes that have been designed for longer shelf life, such as those using modified atmosphere packaging or preservatives, may be stored at ambient temperatures before shipping. Distribution logistics are carefully planned to ensure that cakes reach their destination in perfect condition. Large-scale cake manufacturers work with refrigerated trucking fleets and logistics providers to manage transportation efficiently. Cakes are loaded onto pallets and organized based on their destination, with detailed inventory tracking ensuring that products arrive at the correct locations. In some cases, cakes are shipped directly to supermarkets, bakeries, or food service providers, while others are sent to central warehouses for further distribution. To minimize damage during transit, cakes are packed in sturdy shipping containers designed to absorb vibrations and prevent movement inside the truck. Upon arrival at their final destination, cakes are unpacked and stocked on store shelves or refrigerated display cases. Retailers follow strict storage guidelines to maintain freshness, ensuring that temperature-sensitive cakes are kept in chilled conditions and that all products are rotated based on their expiration dates. Many cakes are sold in pre-packaged formats, while others are displayed in bakery sections where customers can purchase whole cakes or slices. Supermarkets and bakery chains often use just-in-time inventory management systems to minimize waste and ensure a steady supply of fresh cakes. While the majority of factory-made cakes are mass-produced for supermarkets and retail stores, some facilities specialize in producing cakes for commercial bakeries, restaurants, and catering businesses. These cakes are often supplied in bulk, either as frozen cakes that can be thawed and decorated on site, or as partially finished products that can be customized before serving. This flexibility allows bakeries and food service providers to offer fresh cakes without the need for extensive in-house baking operations. The industrial cake making process has evolved significantly over the years, incorporating advanced automation, robotics, and data-driven quality control systems to improve efficiency and consistency. Modern factories utilize artificial intelligence and machine learning to analyze production data, predict maintenance needs, and optimize ingredient usage. Automated production lines can run continuously with minimal human intervention, reducing labor costs and increasing output capacity. One of the most significant innovations in large-scale cake production is the development of high-speed depositing and baking systems. Traditional cake production required separate steps for mixing, portioning, and baking, but modern inline systems integrate these processes seamlessly. For example, continuous mixing systems automatically adjust ingredient ratios based on real-time monitoring, ensuring that each batch maintains the perfect consistency. Depositing machines equipped with servo-driven technology can rapidly change portion sizes, allowing for the production of different cake varieties on the same production line. Baking technology has also advanced, with energy-efficient ovens that use infrared heating and precision airflow systems to achieve uniform baking. These ovens are designed to minimize heat loss, reducing energy consumption while maintaining consistent product quality. Some modern bakeries use hybrid ovens that combine conventional and microwave heating to speed up the baking process without compromising texture. In addition to traditional cakes, many factories produce specialty cakes that cater to specific dietary needs and preferences. Gluten-free cakes, for example, require dedicated production lines to prevent cross-contamination with wheat flour. These cakes use alternative flours, such as rice flour, almond flour, or tapioca starch, along with modified stabilizers to achieve the desired texture. Similarly, vegan cakes are made without eggs or dairy, relying on plant-based substitutes such as flaxseed, aquafaba, and non-dairy milk. Sugar-free and low-carb cakes are also growing in popularity, utilizing sugar alcohols or natural sweeteners like stevia to replace traditional sugar. The rise of personalized and custom cakes has led some factories to develop on-demand printing and decoration technologies. Edible ink printers can create intricate designs, logos, or images directly onto cake surfaces, making them ideal for special occasions or corporate branding. Robotic decorators equipped with artificial intelligence can replicate complex piping patterns, allowing for mass customization with minimal human intervention. Some facilities even offer direct-to-consumer cake ordering services where customers can customize flavors, fillings, and decorations before the cake is produced and shipped. Despite the high level of automation in modern cake production, human oversight remains essential to ensure quality and address any potential issues that arise during manufacturing. Skilled food technologists and quality assurance teams continuously monitor production parameters, conduct taste tests, and refine recipes to maintain consistency. Regular equipment maintenance and cleaning schedules are strictly followed to prevent contamination and ensure compliance with food safety standards. Sustainability is an increasing focus in the cake manufacturing industry, with many companies adopting eco-friendly practices to reduce their environmental impact. Ingredient sourcing has shifted towards sustainable palm oil, fair trade cocoa, and locally sourced dairy to support ethical farming practices. Factories are also investing in waste reduction strategies, such as repurposing cake scraps into secondary products like cake pops, or repackaging unsold cakes into discount bakery items. Some manufacturers have implemented water recycling systems and energy-efficient lighting to further minimize their carbon footprint. Packaging innovation is another area of focus, with a shift toward biodegradable and recyclable materials. Traditional plastic cake containers are being replaced with compostable trays, paper-based wraps, and plant-derived biofilms that maintain freshness while reducing plastic waste. Smart packaging solutions, such as freshness indicating labels and QR codes that provide traceability information, are also being explored to enhance the consumer experience. The demand for factory-made cakes continues to grow globally, driven by changing consumer lifestyles, convenience, and the increasing popularity of ready-to-eat desserts. Emerging markets are seeing a surge in industrial cake production as urbanization and income growth lead to higher demand for packaged bakery products. In response, cake manufacturers are expanding their production capacity, investing in new facilities, and adapting their offerings to regional taste preferences. The future of cake manufacturing is expected to see even greater advancements in automation, customization, and sustainability. 3D food printing technology is being explored as a potential innovation that could revolutionize cake decoration and design. AI-driven recipe development could allow manufacturers to create entirely new flavor profiles based on consumer preferences and sensory data. As consumer awareness of health and nutrition grows, factories may develop functional cakes fortified with protein, fiber, or probiotics to cater to evolving dietary trends. One of the most crucial aspects of large-scale cake manufacturing is maintaining absolute consistency across every batch. Consumers expect the same taste, texture, and appearance every time they purchase a cake from a particular brand, and this requires precise control over every stage of production. Factories employ automated recipe management systems that digitally store exact formulations, ingredient ratios, and process parameters. These systems interface directly with mixing and processing equipment, ensuring that every batch is prepared with the same level of precision. Advanced sensors monitor temperature, humidity, and ingredient dispersion, automatically adjusting machine settings if any deviations are detected. Mixing remains one of the most technologically advanced steps in the industrial cake production process. Continuous mixers, which operate non-stop to produce an unbroken stream of batter, have revolutionized large-scale baking. These machines ensure that ingredients are thoroughly combined without overworking the batter, preserving the delicate structure needed for cakes. In some cases, aeration systems introduce controlled amounts of air into the batter to achieve specific textures. The density and fluffiness of sponge cakes, for instance, depend on the precise incorporation of air during mixing. Factories may also use vacuum mixing technology to remove excess air bubbles and prevent inconsistencies. Once the batter is perfectly blended, it is transferred through high-speed piping systems to the depositing stations. These machines dispense exact portions of batter into baking molds, trays, or individual paper cups for cupcakes. The speed and precision of depositing machines play a critical role in maintaining efficiency, as even a small miscalculation in portioning can lead to product defects or waste. Some depositors use volumetric control, ensuring each mold receives an identical amount of batter, while others rely on piston-driven mechanisms to regulate flow. Factories that produce multiple cake varieties may use multi-head depositing machines capable of filling different molds simultaneously. At this stage, additional mix-ins or toppings may be incorporated. Fruit pieces, chocolate chips, or nuts are often added either before or after depositing, depending on the desired distribution within the cake. Some factories use automated dispensing units that sprinkle toppings evenly across the surface, while others employ injection systems that insert fillings into the center of the cake batter before baking. These injection methods are commonly used for filled cupcakes or specialty cakes with jam, custard, or chocolate centers. The baking process itself is highly controlled, with industrial ovens engineered to ensure even heat distribution. Tunnel ovens, which operate on a conveyor belt system, are the most commonly used in large-scale cake manufacturing. These ovens feature multiple temperature zones that gradually heat the cakes as they move through the baking chamber. The initial phase of baking involves rapid heat transfer to activate leavening agents and promote expansion. As the cakes progress through the oven, moisture is gradually released, setting the structure while maintaining softness. Humidity control is a critical factor in industrial baking. Cakes that lose too much moisture too quickly may become dry, while excess humidity can lead to underbaking or structural collapse. Factories use steam injection systems within ovens to maintain optimal baking conditions. Convection fans circulate hot air evenly, preventing hotspots and ensuring consistent coloration. Some advanced ovens incorporate infrared or microwave-assisted heating to accelerate baking times without compromising quality. Once the cakes emerge from the ovens, they must be cooled carefully to avoid textural inconsistencies. Cooling conveyors transport cakes through controlled environments where temperature and airflow are meticulously regulated. Spiral cooling systems, which maximize space efficiency by stacking conveyors in a vertical spiral, allow for gradual cooling while optimizing factory floor space. Some manufacturers use rapid cooling tunnels equipped with gentle air currents to quickly stabilize cakes intended for immediate packaging. At this stage, cakes may be trimmed, shaped, or portioned according to product specifications. High-speed ultrasonic slicing machines are used for precision cutting, ensuring that each slice maintains a clean edge without crumbling. For layer cakes, industrial slicers divide cakes horizontally, preparing them for filling and stacking. Cakes that require shaping, such as sheet cakes for pre-cut squares, are passed through automated cutting systems that use rotating blades or water jet technology for perfect uniformity. The decoration process is where cakes truly come to life, transforming from simple baked goods into visually appealing products ready for the market. Large-scale factories utilize a combination of robotic systems, automated icing machines, and human decorators for final touches. Buttercream, fondant, or chocolate coatings are applied using enrobing machines or precision icing nozzles. Rotary icing machines create smooth, consistent layers of frosting, while airbrush systems add gradients of color for a professional finish. For cakes requiring intricate designs, robotic decorators equipped with multi-axis arms can replicate complex piping patterns, flowers, or lettering with remarkable accuracy. These machines are programmed to follow specific designs stored in digital templates, allowing manufacturers to mass-produce cakes with customized elements. Some factories use edible ink printers to apply high-resolution images or logos onto cake surfaces, a popular technique for themed birthday cakes and corporate branding. Toppings and embellishments such as sprinkles, chocolate curls, or fruit slices are applied using automated dispensers. Some cakes may pass through a drizzling station where thin streams of chocolate or caramel are added for decorative effect. Cakes requiring additional layers of decoration, such as fondant appliques or edible figurines, are assembled by skilled workers in specialized decoration zones within the factory. Final quality control checks are conducted before packaging. Cakes are inspected for uniformity in shape, frosting consistency, and overall presentation. Some factories employ X-ray scanners and metal detectors to identify potential contaminants or foreign objects within the cakes. Weight sensors verify that each cake meets precise product specifications, and random sampling is conducted for taste testing and texture analysis. Packaging plays a vital role in preserving cake freshness and ensuring product protection during transportation. Depending on the type of cake, various packaging methods are employed. Flow wrapping machines encase individual cakes in airtight plastic film, extending shelf life by preventing exposure to air and moisture. Larger cakes may be placed in rigid plastic containers or cardboard boxes with clear windows for visual appeal. For frozen or refrigerated cakes, vacuum-sealed packaging is often used to lock in freshness. Modified atmosphere packaging, which replaces oxygen with nitrogen or carbon dioxide, helps prevent mold growth and extends shelf stability. Cakes destined for international markets may undergo additional protective measures, such as temperature-controlled shipping containers or specialized packaging to prevent movement during transit. Once packaged, cakes are palletized and loaded onto distribution trucks. Logistics teams coordinate shipments to ensure that products reach their destinations promptly. Some manufacturers supply cakes directly to retail stores, while others distribute them through central warehouses for regional distribution. Refrigerated transport is essential for cakes with perishable ingredients, while shelf-stable varieties are transported under standard conditions. The journey of a cake from the factory to the consumer's table is a testament to the efficiency and precision of modern food manufacturing. The combination of automation, rigorous quality control, and advanced baking technologies ensures that every cake maintains the same high standard of taste and appearance. As consumer preferences evolve, factories continue to innovate, developing new flavors, healthier alternatives, and environmentally sustainable production methods. As cakes leave the factory and make their way to retail stores, bakeries, and food service providers, a highly efficient distribution network ensures that they arrive in perfect condition. Logistics teams work closely with transportation providers to maintain strict temperature controls for cakes that require refrigeration. Cold chain management is essential for ensuring that cakes with fresh cream, custard, or perishable fillings remain safe and retain their intended texture. Refrigerated trucks are equipped with sensors that monitor temperature and humidity levels throughout the journey, providing real-time data to ensure compliance with food safety regulations. For cakes that are shelf-stable, such as packaged sponge cakes, pound cakes, or snack cakes, transportation is more flexible. These products are typically stacked in cartons and palletized to maximize space efficiency. Distribution centers receive shipments and sort cakes based on their final destinations, whether they are headed to supermarkets, convenience stores, or wholesale suppliers. In some cases, cakes are sent to intermediary facilities where additional labeling, repackaging, or regional customization takes place before reaching store shelves. Retailers follow strict inventory management practices to ensure that cakes are sold within their optimal freshness period. Supermarkets and large bakery chains use electronic tracking systems that monitor stock levels and automatically reorder cakes as needed. Cakes with shorter shelf lives are often placed in refrigerated bakery sections, while long-lasting snack cakes are displayed in standard grocery aisles. In many cases, cakes are rotated based on expiration dates to minimize waste, with older stock sold first through strategic shelving placement. For specialty cakes that require customization, such as birthday cakes or event cakes, factories often provide pre-baked cake bases that can be decorated in-store. Retail bakeries receive plain sponge layers, ready-made buttercream, and pre-mixed fillings that allow decorators to assemble and personalize cakes according to customer requests. This hybrid approach combines the efficiency of factory baking with the creative flexibility of in-store decoration. Some supermarket bakeries even utilize edible printing technology to create personalized cake designs on demand, using high-resolution printers that apply edible ink onto sheets of fondant or rice paper. The demand for factory-produced cakes continues to grow as consumers seek convenient, high-quality desserts for various occasions. Large-scale cake manufacturers constantly innovate to meet changing market preferences, introducing new flavors, textures, and dietary options. Seasonal cakes, such as holiday-themed cakes or limited edition flavors, are planned months in advance, with factories adjusting their production schedules to accommodate demand spikes. These cakes often feature special packaging, festive decorations, or unique flavor combinations that align with holiday traditions and cultural celebrations. One of the biggest trends in modern cake manufacturing is the development of healthier alternatives. Consumers are increasingly looking for reduced sugar, gluten-free, and plant-based cake options that cater to dietary restrictions and health-conscious lifestyles. Factories have adapted by reformulating traditional recipes, replacing refined sugars with natural sweeteners like stevia or monk fruit, and using alternative flours such as almond flour or coconut flour to create gluten-free variations. These formulations require precise adjustments to maintain the desired texture and taste, as the absence of gluten or sugar can affect the structural integrity of cakes. Another emerging trend is the use of functional ingredients to enhance the nutritional profile of cakes. Factories are experimenting with protein-fortified cakes, fiber-rich formulations, and probiotic-infused desserts that offer health benefits beyond traditional indulgence. Cakes with added omega-3 fatty acids, collagen, or antioxidant-rich ingredients appeal to consumers who want to enjoy sweet treats without compromising on wellness goals. Manufacturers use encapsulation technology to protect sensitive nutrients during baking, ensuring that functional ingredients remain effective even after exposure to heat. Sustainability is a growing priority in cake manufacturing, with companies striving to reduce their environmental footprint at every stage of production. Many factories have implemented waste reduction programs that repurpose cake trimmings into new products, such as cake pops, cookie bases, or cereal bar inclusions. Some manufacturers donate surplus cakes to food banks or partner with organizations that distribute baked goods to communities in need. Wastewater treatment systems, energy-efficient baking ovens, and recyclable packaging materials further contribute to sustainability efforts. The shift toward eco-friendly packaging is particularly significant as traditional plastic cake containers contribute to global plastic waste issues. Factories are exploring biodegradable alternatives, such as plant-based plastics, compostable trays, and paper-based packaging with food-safe coatings. Some manufacturers have developed innovative packaging solutions that extend shelf life without relying on excessive plastic, using breathable film technology that regulates moisture levels to prevent staleness. Smart packaging, which includes QR codes that provide traceability information or freshness indicators that change color based on product age, is also gaining traction in the industry. The future of cake manufacturing is expected to be shaped by advancements in automation, artificial intelligence, and customization technology. AI-powered production lines are already capable of self-adjusting parameters based on real-time data, optimizing mixing, baking, and cooling processes for maximum efficiency. Machine learning algorithms analyze consumer purchasing patterns to predict demand fluctuations, allowing factories to adjust production schedules accordingly. 3D food printing is another exciting development that could revolutionize cake decoration and customization. Some companies are experimenting with 3D printed cake designs, where intricate sugar sculptures, chocolate accents, or even full cake layers are printed layer by layer. This technology opens up new possibilities for personalized cakes, allowing consumers to design unique cake structures that were previously impossible to achieve with traditional decorating techniques. Another potential breakthrough is the use of blockchain technology to improve transparency in the supply chain. By implementing blockchain tracking systems, cake manufacturers can provide consumers with detailed information about ingredient sourcing, production dates, and quality control measures. This level of traceability builds trust with consumers and ensures compliance with food safety regulations, especially in an era where ethical sourcing and ingredient transparency are increasingly important. As the global cake market continues to expand, manufacturers must adapt to diverse consumer preferences across different regions. In some countries, lighter sponge cakes with whipped cream fillings are preferred, while in others, dense and rich chocolate cakes dominate the market. Factories tailor their production lines to accommodate regional tastes, incorporating local ingredients and traditional flavors into their offerings. The rise of e-commerce and direct-to-consumer cake delivery services has further transformed the industry, with many factories now offering online ordering and home delivery options. The large-scale production of apple pies in a factory begins long before the first piece of dough is rolled or the first apple is peeled. The process starts with careful ingredient selection and sourcing, ensuring that only high-quality raw materials are used to maintain consistency in texture, flavor, and appearance. Apples are the most essential component, and factories work with orchards and suppliers to secure varieties that hold their shape during baking. Granny Smith, Honeycrisp, and Golden Delicious are among the most commonly used apple varieties due to their balance of tartness and sweetness, as well as their ability to remain firm when exposed to heat. These apples are harvested at peak ripeness, stored in temperature-controlled environments, and transported in bulk to the manufacturing facility. Before arriving at the factory, apples go through an initial sorting and washing process at agricultural processing plants. They are visually inspected, and any damaged or overly bruised apples are removed. Automated sorting systems use laser scanning and weight sensors to classify apples by size, ensuring uniformity in the final product. Once they reach the pie manufacturing facility, apples are subjected to another round of cleaning, where they pass through water jets, brushes, and food-safe sanitizing solutions to remove any remaining dirt, wax, or pesticide residues. Flour is another key ingredient, forming the base of the pie crust. The type of flour used depends on the desired texture of the crust. Factories often blend different flours to achieve the perfect balance of tenderness and flakiness. Large silos store refined wheat flour, which is sifted and aerated before use. Fat sources, such as butter, vegetable shortening, or margarine, are also prepared in bulk, often stored in temperature-controlled tanks or solid blocks that will later be incorporated into the dough. Sugar, cinnamon, nutmeg, and other spices are pre-measured in precise quantities to ensure flavor consistency across every batch. Before production begins, factory equipment undergoes a rigorous sanitation process. Conveyor belts, mixers, dough sheeters, peeling machines, and baking ovens are all thoroughly cleaned and sterilized to prevent cross-contamination. Strict hygiene protocols are in place, and workers handling ingredients wear protective gloves, hairnets, and sanitized uniforms. Automated ingredient dispensers are calibrated to ensure the correct proportions are used, minimizing human error and improving efficiency. The first major step in the pie-making process is preparing the apples. Massive apple peeling machines process hundreds of apples per minute, using rotating blades to remove the skin efficiently. Some machines employ steam peeling, which uses high-pressure steam to loosen the skin before it is brushed off, reducing waste and preserving more of the fruit's flesh. After peeling, apples are quickly cored and sliced into uniform pieces. Factories use industrial slicers that cut apples into precise shapes, thin slices for traditional pies, or chunkier pieces for rustic-style pies. Once sliced, apples move along conveyor belts to be treated with an antioxidant solution, preventing browning caused by oxidation. This solution, typically a blend of ascorbic acid, vitamin C, and citric acid, ensures that apples maintain their natural color and freshness throughout the production process. The prepared apple slices are then transported to large mixing vats, where they are combined with sugar, spices, and thickening agents such as cornstarch or modified food starch. This ensures that the filling will have the right consistency, preventing it from becoming too runny or too dry during baking. The mixing process is carefully timed to distribute spices evenly without breaking down the apple slices. While the filling is being prepared, the pie crust is mixed and rolled out. In large-scale production, dough preparation is a highly automated process that ensures uniformity across thousands of pies. Ingredients such as flour, fat, water, and salt are combined in massive industrial mixers equipped with precision temperature controls. The temperature of the fat is crucial. If it is too warm, the dough will become overly soft and lose its flaky texture. If it is too cold, it will not incorporate properly. Factories use chilled water and climate-controlled rooms to maintain the ideal dough consistency. Once mixed, the dough is fed into an automated sheeting machine that rolls it to the exact thickness required for pie crusts. The dough is then cut into circular shapes using rotary cutters, ensuring every crust is the perfect size. Some factories employ laminating techniques to create extra layers in the dough, mimicking the effect of handmade flaky pie crusts. Excess dough from the cutting process is collected, reworked, and reintegrated into the next batch to minimize waste. The next step is assembling the pies. Conveyor belts transport the bottom crusts to the filling stations, where the prepared apple mixture is deposited into each pie shell. Factories use volumetric filling machines to ensure that each pie receives the exact amount of filling, preventing overflow or underfilling. The filling must be evenly distributed to prevent uneven baking, and any excess liquid is drained to keep the crust from becoming soggy. Once the filling is in place, the top crust or lattice is added. Factories use automated dough placers to position pre-cut dough circles onto the pies, and crimping machines press the edges together, sealing the filling inside. For lattice-top pies, robotic systems weave strips of dough in an intricate pattern, replicating the handcrafted appearance of traditional home-baked pies. Some factories also produce streusel-topped apple pies, where a crumbly mixture of butter, sugar, and flour is sprinkled over the filling before baking. Before the pies enter the ovens, finishing touches are applied. Some pies receive an egg wash or milk wash to create a glossy, golden brown crust, while others are dusted with cinnamon sugar for added flavor and visual appeal. Venting machines create small slits in the top crust, allowing steam to escape during baking and preventing the filling from bursting through the crust. The baking process is one of the most carefully controlled steps in pie manufacturing. Industrial ovens operate at precisely calibrated temperatures to ensure even baking without drying out the filling or burning the crust. Tunnel ovens, which use conveyor belts to move pies through different heat zones, are the most common in large-scale production. The first zone rapidly heats the pies to set the crust and activate the thickening agents in the filling. The middle zone maintains consistent baking temperatures, allowing the apples to soften while the crust becomes golden and flaky. The final cooling zone gradually reduces the temperature to prevent shrinkage or cracking. Once baked, the pies must be cooled before packaging. Factories use cooling tunnels equipped with controlled airflow systems to bring the pies to room temperature quickly and efficiently. This process is crucial. If pies are packaged while still warm, condensation can form inside the packaging, leading to sogginess or mold growth. Spiral cooling conveyors maximize space efficiency, allowing pies to cool gradually without taking up excessive floor space. Before packaging, each pie undergoes a final round of quality control inspections. Vision inspection systems equipped with high-resolution cameras scan each pie for imperfections such as uneven crusts, filling leakage, or discoloration. Weight sensors confirm that each pie meets precise weight specifications, ensuring consistency in every unit. Random samples are pulled for taste testing and texture analysis, verifying that the crust maintains its flakiness and that the apple filling has the right balance of sweetness and spice. After passing quality checks, pies move on to the packaging stage. Factories use automated wrapping machines that encase each pie in protective film or place them in cardboard boxes with clear plastic windows for visibility. Some pies are packaged individually for single-serve portions, while larger family-sized pies are sealed in airtight containers to preserve freshness. Packaging plays a critical role in maintaining the freshness and structural integrity of apple pies as they move through the supply chain. Once the pies have cooled completely, they are transferred to automated packaging lines where they are placed into protective containers. Factories use a variety of packaging methods depending on the type of pie being produced. Whole pies, designed for retail sale, are often placed in sturdy cardboard boxes with clear plastic windows, allowing consumers to see the product while keeping it protected. The boxes are sealed with tamper-evident closures to ensure food safety and compliance with industry regulations. For frozen apple pies, specialized packaging materials are used to prevent freezer burn and moisture loss. These pies are typically wrapped in airtight plastic film before being placed in cartons designed to withstand low temperatures. Vacuum sealing or modified atmosphere packaging techniques may also be used to remove excess oxygen and extend the shelf life of frozen pies. Factories that produce individual-sized apple pies or snack-sized turnovers use flow wrapping machines to encase each product in a flexible plastic film, preserving freshness while allowing for easy transport and handling. Once packaged, each pie is labeled with key product information, including expiration dates, ingredient lists, nutritional facts, and barcodes for inventory tracking. High-speed labeling machines apply these labels with precision, ensuring that they are aligned correctly and free from wrinkles or misprints. In some cases, additional stickers or promotional labels may be applied to highlight seasonal flavors, limited edition varieties, or special offers. Before shipping, a final round of quality control inspections takes place. Automated vision systems scan each packaged pie for defects such as misaligned labels, improper sealing, or signs of damage. Weight sensors confirm that each pie falls within the specified weight range, and metal detectors or X-ray machines are used to identify any potential foreign objects that may have inadvertently entered the production line. Randomized sampling is conducted, with select pies being opened and tested for taste, texture, and consistency to ensure they meet quality standards. Once cleared for distribution, the pies are packed into larger cartons or cases and stacked onto pallets for shipping. Logistics teams coordinate transportation, ensuring that pies reach their destinations in optimal condition. Refrigerated trucks are used for frozen pies, while shelf-stable varieties are transported under standard conditions. Large-scale manufacturers often supply pies to supermarkets, convenience stores, and food service providers, while some factories also produce private label pies for retailers under store brand names. At retail locations, apple pies are stocked in bakery sections, freezer aisles, or snack food displays, depending on their packaging and storage requirements. Supermarkets and bakeries follow strict inventory rotation practices, ensuring that older products are sold first to minimize waste. Some retailers may also offer in-store customization, allowing customers to purchase plain apple pies and add whipped cream, caramel drizzle, or other toppings before serving. In addition to retail distribution, many apple pie manufacturers supply food service businesses, including restaurants, cafeterias, and catering companies. These establishments often receive bulk shipments of pre-baked or frozen pies that can be reheated and served as needed. Some manufacturers also produce partially baked or par-baked pies, which allow food service providers to finish baking the pies in their own ovens for a freshly baked aroma and texture. As consumer preferences evolve, apple pie manufacturers continue to innovate with new flavors, formats, and dietary options. Gluten-free apple pies, for example, use alternative flours such as rice flour or almond flour to accommodate individuals with gluten sensitivities. Vegan apple pies eliminate butter and eggs, using plant-based substitutes such as coconut oil or flaxseed-based thickeners. Sugar-free and low-calorie apple pies cater to health-conscious consumers, replacing refined sugar with natural sweeteners such as stevia or monk fruit extract. Another growing trend in the apple pie industry is the development of artisanal-style products that mimic the appearance and taste of homemade pies while benefiting from large-scale production efficiency. Factories use specialized techniques to create rustic-style crusts, hand-crimped edges, and uneven lattice patterns that give the impression of being handmade. Some manufacturers also experiment with unique fillings, incorporating ingredients such as caramelized apples, bourbon-infused sauces, or spiced pecans to create gourmet variations. The production process has also seen significant advancements in automation and smart manufacturing technology. Modern pie factories utilize AI-driven production systems that monitor real-time data, adjusting mixing times, baking temperatures, and ingredient ratios automatically to ensure consistent results. Predictive maintenance technology helps prevent equipment breakdowns by analyzing performance patterns and scheduling maintenance before issues arise, reducing downtime and increasing efficiency. Sustainability initiatives are becoming increasingly important in the apple pie manufacturing industry. Many factories are adopting eco-friendly practices, such as sourcing apples from local farms to reduce transportation emissions and investing in renewable energy to power production facilities. Waste reduction programs repurpose pie trimmings and excess dough into secondary products, such as pie crust crumbs used for cheesecakes or repackaged as dessert toppings. Some manufacturers donate surplus pies to food banks, helping to combat food waste while supporting community initiatives. Packaging sustainability is another major focus, with companies seeking alternatives to traditional plastic containers. Biodegradable pie trays made from compostable materials, recycled paperboard cartons, and plant-based plastic wraps are being developed to reduce environmental impact. Some manufacturers are exploring edible packaging concepts where a protective sugar-based glaze can replace plastic wrapping while still keeping the pie fresh. The future of apple pie manufacturing is likely to see continued advancements in customization and convenience. Direct-to-consumer models are emerging, where customers can order personalized apple pies online and have them delivered fresh to their doorsteps. Smart kitchen appliances equipped with pie warming technology may become more common, allowing consumers to heat pre-packaged pies to optimal serving temperature with precision settings. 3D food printing technology is also making its way into the baking industry, with the potential to create intricate pie crust designs, decorative elements, and even printed fruit fillings layered in artistic patterns. Artificial intelligence may play a larger role in recipe development, analyzing consumer preferences and market trends to create innovative new apple pie variations. As demand for nostalgic, comforting desserts remains strong, apple pies continue to be a staple in bakeries, supermarkets, and food service establishments worldwide. The balance between tradition and technological advancement allows manufacturers to produce high-quality apple pies on a large scale while preserving the flavors and textures that consumers love. From ingredient sourcing to packaging innovation, every step of the process is designed to deliver a consistently delicious and visually appealing product. After the pies have been packaged and prepared for distribution, the journey from the production line to the consumer's hands becomes a finely tuned logistical operation. Factory staff and automated systems coordinate to load the packaged apple pies onto pallets, where each case is carefully arranged to prevent shifting during transit. This organization ensures that every pie arrives intact, with its decorative finish and flaky crust preserved. Refrigerated transport is utilized for pies that require controlled temperatures, such as those with delicate cream-based toppings or freshly prepared fruit mixtures, while room temperature varieties are shipped in climate-controlled vehicles to avoid any undesirable temperature fluctuations. Throughout this process, detailed tracking systems monitor the location, temperature, and status of shipments, ensuring that any potential issues can be quickly identified and addressed. Within the distribution centers, a well-structured system of inventory management is employed to maintain the integrity of the pies. Automated scanning and tracking devices help manage stock levels, and storage facilities are organized in a manner that optimizes space, while ensuring that pies are not exposed to excessive light or temperature changes. When orders are processed, computer-controlled systems select the appropriate batches, ensuring that the older stock is distributed first to prevent any waste. In high-demand periods, such as during holidays or seasonal promotions, the system automatically adjusts to accommodate increased volumes, demonstrating the scalability and efficiency of modern industrial food production. Retailers receive the shipments with the assurance that every pie meets strict quality criteria and that the production process adheres to both safety regulations and customer expectations. As consumer trends shift towards healthier and more diverse food options, apple pie manufacturers are continuously refining their recipes and production methods to cater to these evolving demands. One notable trend is the incorporation of organic apples and natural sweeteners. Factories are increasingly sourcing apples from certified organic orchards and experimenting with honey, maple syrup, or agave nectar as alternatives to refined sugars. These innovations are not only designed to meet the nutritional preferences of health-conscious consumers, but also to offer a richer and more nuanced flavor profile. The challenge of maintaining the perfect consistency in the filling while using these alternative ingredients has led to the development of specialized processing techniques. For example, adjustments in the proportions of thickening agents and the precise timing of the mixing process are made to account for the different moisture and sugar levels in organic produce and natural sweeteners. In response to growing concerns over allergen exposure, many apple pie factories have established dedicated production lines for allergen-free products. These production lines are segregated from the main processing areas. The creation of Reese's Peanut Butter Cups is a meticulous process that begins with the careful selection and preparation of peanuts, the cornerstone of the product's distinctive flavor and texture. This journey starts with sourcing high-quality peanuts, primarily from regions renowned for their optimal growing conditions, such as Georgia and Texas. These areas provide the ideal climate and soil composition, resulting in peanuts with the desired size, flavor, and oil content essential for the signature Reese's taste. Upon arrival at the manufacturing facility, the peanuts are subjected to a rigorous inspection process. Advanced optical sorting machines, equipped with high-resolution cameras and sensors, meticulously scan each peanut, identifying and removing any that are discolored, misshapen, or contaminated with foreign materials. This ensures that only the finest peanuts proceed to the next stage, maintaining the high-quality standards synonymous with Reese's products. Following sorting, the peanuts undergo a thorough cleaning process. They are funneled through a series of air classifiers and vibrating screens that effectively remove dirt, stones, and other debris. Some facilities may also employ water baths or steam cleaning methods to ensure an even higher level of cleanliness. This step is crucial, as any residual impurities could adversely affect the flavor and safety of the final product. The next phase involves roasting the cleaned peanuts to develop their rich, nutty flavor and achieve the desired texture. Industrial roasters, such as continuous belt roasters or rotary drum roasters, are employed to ensure even roasting. The peanuts are exposed to temperatures ranging from 320 degrees Fahrenheit to 350 degrees Fahrenheit for a specific duration, typically between 30 to 60 minutes. The exact time and temperature are carefully controlled and adjusted based on factors like peanut variety and moisture content to achieve the optimal roast profile. During roasting, the Maillard reaction, a chemical interaction between amino acids and reducing sugars, occurs, contributing to the development of complex flavor compounds and the characteristic golden brown color of the peanuts. Continuous monitoring of temperature and airflow within the roasters ensures uniform roasting and prevents over or undercooking, which could compromise the flavor and quality of the peanut butter filling. Once roasting is complete, the peanuts are rapidly cooled to halt the cooking process and preserve their flavor profile. This is typically achieved by passing the hot peanuts through cooling conveyors equipped with powerful fans that circulate ambient air. Rapid cooling prevents the peanuts from continuing to cook from residual heat, which could lead to undesirable flavor changes or textural issues. After cooling, the peanuts are transferred to blanching machines, where their skins are removed. Blanching involves exposing the peanuts to steam or hot air to loosen the skins, followed by mechanical rubbing or abrasion to peel them away. This step is essential, as peanut skins can impart a bitter taste and affect the smoothness of the peanut butter. The blanched peanuts are then inspected once more to ensure all skins and any remaining impurities have been effectively removed. The blanched peanuts are now ready for grinding, a critical step in transforming them into the creamy peanut butter that fills each Reese's cup. The peanuts are fed into industrial grinders, which consist of a series of grinding plates or mills that progressively reduce the peanut particles to the desired consistency. The initial grinding stage breaks the peanuts into coarse pieces, while subsequent stages further refine the texture, resulting in a smooth, creamy peanut butter. Throughout the grinding process, the peanut's natural oils are released, contributing to the creamy consistency of the peanut butter. To achieve the perfect texture and prevent oil separation, stabilizers such as hydrogenated vegetable oils may be added. These stabilizers help maintain the emulsion of peanut solids and oils, ensuring the peanut butter remains smooth and spreadable over time. Temperature control during grinding is paramount. Excessive heat generated by friction can alter the flavor and consistency of the peanut butter. To mitigate this, cooling systems are integrated into the grinding equipment, maintaining the peanut butter at an optimal temperature and preserving its quality. Once the peanut butter reaches the desired consistency, it is transferred to stainless steel storage tanks equipped with agitation systems. These systems keep the peanut butter uniformly mixed, preventing the settling of solids and ensuring consistency across batches. The storage tanks are part of a closed system that protects the peanut butter from exposure to air and potential contaminants, preserving its freshness and flavor until it is needed for the next stage of production. Now, it's time to delve into the preparation of the chocolate coating that envelops the peanut butter filling, giving Reese's peanut butter cups their iconic taste and texture. The chocolate used is a carefully formulated blend designed to complement the peanut butter's flavor while providing a smooth and satisfying mouthfeel. The process begins with the selection of premium cocoa beans, sourced from regions known for their high-quality cocoa production, such as West Africa and South America. These beans are fermented and dried at their origin to develop the foundational flavor characteristics essential for quality chocolate. Upon arrival at the manufacturing facility, the cocoa beans undergo roasting, a process that further develops their flavor and reduces moisture content. Industrial-scale roasters, similar to those used for peanuts, are employed to ensure even roasting. The beans are roasted at temperatures between 250 degrees Fahrenheit to 320 degrees Fahrenheit for durations ranging from 30 to 60 minutes, depending on the desired flavor profile. Continuous monitoring ensures consistency and prevents over-roasting, which could impart bitter notes to the chocolate. After roasting, the cocoa beans are cooled and subjected to winnowing, a process that removes the outer shells, leaving behind the valuable cocoa nibs. These nibs are then ground into cocoa mass, also known as cocoa liquor, which serves as the base for all chocolate products. The grinding process generates heat, causing the cocoa butter within the nibs to melt and form a liquid mass. To create milk chocolate, the variety used in Reese's peanut butter cups, the cocoa mass is combined with specific proportions of sugar, milk solids, and additional cocoa butter. This mixture undergoes refining, where it is passed through a series of rollers to reduce particle size, resulting in a smoother texture. Achieving the optimal particle size is crucial, as it influences the mouthfeel and overall quality of the chocolate. Following refining, the chocolate mixture undergoes conching, a process involving continuous mixing and aeration at controlled temperatures. Conching serves multiple purposes. It further smooths the texture, develops flavor by promoting the evaporation of undesirable volatile compounds, and ensures a homogeneous blend of ingredients. The duration and temperature of conching are carefully controlled, with longer conching times typically resulting in superior flavor development. Once conching is complete, the chocolate is tempered to stabilize its crystalline structure. Tempering involves carefully cooling and reheating the chocolate to specific temperatures, encouraging the formation of stable cocoa butter crystals. Proper tempering ensures that the chocolate sets with a glossy finish, has a satisfying snap, and resists blooming, a condition where fat or sugar crystals rise to the surface. creating a dull or streaked appearance. The tempered chocolate is maintained at a precise temperature in holding tanks, ready for the enrobing process. These tanks are equipped with gentle agitation systems to keep the chocolate uniformly mixed and at the correct viscosity for coating the peanut butter filling. But up next is the integration of the peanut butter filling and the chocolate coating, a process that demands precision and synchronization to achieve the perfect balance between the two components. Specialized machinery is employed to deposit measured amounts of peanut butter onto a base layer of chocolate, ensuring consistency in size and weight for each cup. The process begins with the formation of the chocolate shell. Molds, typically made of polycarbonate or stainless steel, are filled with a specific amount of tempered milk chocolate, dispensed through precision-controlled nozzles. These molds then pass through a vibration station which ensures the chocolate evenly coats the bottom and sides of the mold cavity. This vibration also helps eliminate any air bubbles that could compromise the integrity or appearance of the finished product. The amount of chocolate deposited and the intensity of vibration are both tightly regulated, ensuring uniformity across thousands of cups produced per hour. Once the molds are coated, they are inverted and lightly spun in a controlled environment. This inversion allows excess chocolate to drain off while still leaving a consistent layer adhered to the inner surfaces of each mold. This stage is crucial. Too much chocolate can overwhelm the peanut butter filling, and too little can lead to structural failure of the cup during demolding or packaging. The molds then proceed through a cooling tunnel, typically kept at temperatures between 45 degrees Fahrenheit and 55 degrees Fahrenheit. The cooling phase ensures that the chocolate shell partially sets to the correct hardness before it receives the peanut butter filling. As the molded chocolate shells emerge from the cooling tunnel, they are transported to the filling station. Here, a high-speed depositor arm, equipped with precision temperature and viscosity control, deposits the peanut butter filling into each partially set chocolate cup. The filling temperature is typically maintained between 85 degrees Fahrenheit and 95 degrees Fahrenheit, warm enough to flow smoothly, but cool enough not to melt or deform the chocolate shell. The depositor is calibrated to deliver an exact volume of filling per cup, down to a fraction of a milliliter. This exactness is essential for product consistency and for ensuring that the peanut butter doesn't spill over the edges when the top chocolate layer is added. The formulation of the peanut butter filling used in Reese's is slightly different from traditional peanut butter. It is intentionally thicker and drier in consistency, achieved by controlling the moisture content and fat levels during the grinding and mixing process. This formulation helps the filling maintain its shape during deposition and ensures it doesn't mix into or bleed through the surrounding chocolate. The peanut butter also contains a precise blend of sugar, salt, and stabilizers, all tailored to produce the sweet, slightly salty, and crumbly texture unique to Reese's cups. After the filling is deposited, the molds move on to receive the final chocolate layer. This top layer of tempered chocolate is again dispensed with precision, covering the peanut butter entirely and sealing the cup. The exact thickness of this layer is calibrated to ensure a perfect balance between the two flavors and to provide structural integrity once the product is unmolded. If the chocolate top is too thin, it risks cracking during cooling and handling. Too thick, and it throws off the flavor harmony. The fully assembled peanut butter cups then enter a second cooling tunnel. This tunnel is longer and colder than the first, typically operating between 35 degrees Fahrenheit and 45 degrees Fahrenheit. Here, the final chocolate layer sets completely, bonding with the underlying components and solidifying the cup into its final form. Conveyor belts inside the tunnel are carefully speed regulated so that the cups spend the exact amount of time needed to fully crystallize the cocoa butter without overcooling, which could lead to bloom or textural issues. As the cooled and fully set cups exit the tunnel, they are transported to the demolding station, This is a delicate and crucial phase where the now solid chocolate cups must be removed from their molds without cracking, chipping, or leaving any residue behind. Modern factories use pneumatic or mechanical release systems that gently flex the molds while applying a quick burst of air from underneath each cavity. This loosens the cups and lifts them onto a secondary conveyor without physical contact from human hands, preserving hygiene and preventing product damage. Now it's time to go into the inspection and quality control stage, a multi-layered process where each Reese's peanut butter cup is evaluated for conformity, appearance, and safety. As the demolded cups travel along the inspection conveyor, they pass through high-resolution vision systems equipped with artificial intelligence software that scans for imperfections. This includes checking for chips in the chocolate, uneven layers, off-center fillings, or improperly formed edges. Cups that do not meet the strict visual criteria are automatically rejected by air jets that direct them off the main line and into collection bins for disposal or reprocessing, depending on company policy and food safety regulations. In addition to visual checks, random samples are pulled at regular intervals for more in-depth testing. These samples are weighed to ensure they meet exacting product specifications. Other tests may include breaking the cup in half to examine the internal peanut butter to chocolate ratio, or using texture analyzers that measure the product's resistance to pressure, an indicator of proper tempering and filling density. Chemical testing is also conducted regularly to verify the correct balance of sugar, moisture, fat, and salt in the filling. These tests are often performed in on-site quality control laboratories, where technicians run batch samples through a range of analytical equipment, such as moisture analyzers, gas chromatographs, and spectrophotometers. If any irregularities are found, production is paused, and corrective measures are implemented. This could mean recalibrating a depositor nozzle, adjusting roasting temperatures for peanuts, or even reviewing the supply chain for ingredient inconsistencies. But up next is the packaging stage, which begins with the alignment of the peanut butter cups into lanes that feed into high-speed wrapping machines. These machines are capable of wrapping hundreds of cups per minute, and they must do so without damaging the fragile chocolate shell. The wrapper material is typically a laminated foil paper composite, selected for its barrier properties against oxygen, moisture, and light, all of which can degrade product quality over time. Each wrapper is printed with the Reese's branding, product information, batch codes, and expiration dates using thermal or inkjet printers. As the cups enter the wrapping station, they are placed onto rotating belts that synchronize with the wrapper feed. A roll of pre-printed wrapping film is continuously pulled into position, cut to size by high-speed blades, and sealed around each cup using heated crimpers. The sealing temperature and pressure must be carefully controlled to ensure an airtight seal without melting the chocolate inside. Once wrapped, the cups are grouped for secondary packaging. They may be placed in cardboard sleeves, plastic trays, or directly into multi-unit bags, depending on the product configuration. These groups are then placed into larger cartons for shipping. Before sealing, a final barcode scanner checks each item to confirm it matches the correct SKU and batch. Any errors trigger an automatic halt in the packing line to prevent cross-contamination between different product types. Every carton is weighed and scanned one final time before being sealed, labeled, and moved to the warehouse staging area. From here, pallets of Reese's peanut butter cups are logged into an inventory system and scheduled for distribution to retail locations across the country. Every step from peanut to pallet is tracked with traceability data, ensuring full accountability throughout the production cycle. Now it's time to go into the warehousing and distribution phase of Reese's peanut butter cup production, where the finished products transition from tightly controlled factory environments to large-scale logistics operations. Once the individually wrapped and secondary packaged cups are assembled into master cartons, these cartons are loaded onto pallets. Each pallet holds a predefined number of cartons, strategically arranged to optimize space while maintaining product integrity during transport. Automated palletizers equipped with robotic arms or gantry systems handle this process with precision, stacking cartons with minimal human intervention to ensure efficiency and reduce labor costs. Once a pallet is completed, it's secured using high-tensile stretch wrap, often applied via automated rotary arm or turntable wrapping machines. This stretch film not only stabilizes the load, but also provides a moisture and dust barrier, safeguarding the products during storage and shipping. Pallets are then labeled with barcoded shipping tags that include vital information such as product codes, batch numbers, production dates, and destination data. These barcodes are integrated into the factory's centralized inventory management system, allowing for real-time tracking and traceability from the moment a product leaves the production floor. The wrapped and labeled pallets are then moved to climate-controlled storage areas within the facility's warehouse. These storage zones are maintained at stable temperatures, typically between 55 degrees Fahrenheit and 70 degrees Fahrenheit, to ensure the chocolate remains in perfect condition. Extreme heat can cause melting or blooming, while excessive cold may alter texture or create condensation that can compromise the packaging seal. Environmental sensors continuously monitor these storage areas, and any deviation outside preset tolerances triggers alerts for immediate corrective action. Warehouse operations are managed by advanced warehouse management systems, which direct the flow of goods through automated guided vehicles or forklifts, guiding them to the optimal racking locations based on FIFO principles. This ensures older inventory is shipped before newer batches, reducing the risk of aging stock reaching consumers. Some high-output facilities even use fully automated storage and retrieval systems, where robotic cranes handle all inbound and outbound movement of pallets without human inputs. As orders come in from distribution centers, retail chains, or e-commerce platforms, the WMS generates pick lists, directing operators or picking robots to assemble the correct products for shipment. During the picking process, each item's barcode is scanned again to confirm accuracy. Pallets are then loaded onto temperature-controlled trucks or shipping containers, with the logistics team carefully planning routes and loading sequences to match delivery schedules. The transportation phase is critical in preserving product quality. Trucks used to transport Reese's peanut butter cups are often equipped with refrigeration units to maintain stable conditions, especially during warmer months or in hot climates. Real-time GPS tracking and telematics systems allow logistics managers to monitor vehicle locations and environmental conditions inside the trailers, ensuring any issues can be addressed proactively. Once the Reese's cups arrive at regional distribution centers, they're cross-docked or stored temporarily before being sent to individual retail locations. Cross-docking minimizes storage time by immediately transferring incoming goods to outgoing trucks, improving freshness and reducing inventory holding costs. At the retail level, automated shelf replenishment systems and electronic point-of-sale data further refine logistics by signaling when to restock based on actual consumer purchases, closing the loop between factory and final sale. Now it's time to explore the role of factory automation and digital systems that underpin every phase of Reese's peanut butter cup production. From peanut sorting to final product distribution, automation enhances consistency, efficiency, and food safety across the board. At the front end of the process, smart sensors and machine vision systems oversee raw ingredient inspection. These tools can detect flaws invisible to the human eye, such as slight discoloration, mold, or the presence of foreign matter, ensuring that only the highest quality peanuts and cocoa beans enter the process. Programmable logic controllers orchestrate the flow of operations on the production line. These industrial computers are connected to every piece of equipment, from roasters and grinders to depositors and cooling tunnels, and execute real-time instructions based on input data. For example, if a change in peanut moisture content is detected by inline sensors, the PLC can automatically adjust roasting time or temperature to compensate, maintaining flavor consistency. Supervisory control and data acquisition systems provide plant operators with a bird's-eye view of the entire production environment. With these interfaces, managers can monitor batch progress, verify line speeds, track downtime, and receive alerts if any machinery falls out of spec. Every action taken by machines is logged for traceability, which is particularly important for food safety compliance and auditing purposes. Data collected from SCADA systems can also be analysed for continuous improvement, helping to identify bottlenecks, optimise throughput, and reduce energy consumption. Robotics play a crucial role in packaging and material handling. Articulated robotic arms, equipped with suction grippers or vision-guided end effectors, perform tasks such as picking and placing cups into trays, applying labels, or stacking cartons. These robots can work around the clock without fatigue, dramatically improving productivity while maintaining precision and reducing injury risk for human workers. Factory hygiene and sanitation are also managed with the help of automation. Clean-in-place systems are installed throughout the facility to automatically flush and sanitize processing lines between batches. These systems circulate heated cleaning solutions through tanks, pipes, and machinery to remove peanut residue and chocolate buildup, all without disassembling equipment. Sensors measure cleaning effectiveness in real time, ensuring that microbial standards are met and that no allergenic cross-contact occurs between production cycles. But up next is the innovation behind product design and the proprietary formulation that gives Reese's Peanut Butter Cups their legendary status. While the general public recognizes the product for its flavor, texture, and iconic shape, much of the success lies in the precise engineering of ingredients and design. The ratio of peanut butter to chocolate has been refined over decades of experimentation, resulting in a balance that optimizes sweetness, saltiness, creaminess, and firmness. Hershey's R&D teams use texture analysis, sensory panels, and predictive modeling to test thousands of variations in ingredient proportions before locking in a final formula. Ingredient consistency is paramount. For instance, the type of sugar used in the peanut butter filling is selected not just for sweetness, but for its ability to control water activity and crystallization during storage. The salt content is finely tuned to enhance the peanut flavor without becoming overpowering, while milk powder used in the chocolate is selected for both its taste and its emulsifying properties. Even minor fluctuations in these ingredients can affect the final mouthfeel and flavor, which is why tight supplier controls and internal batch testing are enforced. The cup shape and wrapper design are also engineered with precision. The signature fluted edge of each Reese's cup isn't just a visual cue, it aids into molding and adds structural strength. The cups are formed using molds with concentric grooves that create this pattern as chocolate is spun or vibrated up the walls. The wrapper is designed to peel off easily without sticking to the chocolate, which requires selecting specific coatings and materials that interact correctly with cocoa butter at varying humidity levels. In recent years, innovation has also extended to creating new product lines, miniatures, thins, big cups, and seasonal shapes. Each variant requires its own custom set of tooling, depositor calibrations, and process flow adjustments to accommodate differences in fill volume, chocolate thickness, and packaging format. These product changes often involve months of pilot testing on R&D lines before being scaled to full production. Engineers simulate the behavior of chocolate and peanut butter under different conditions using computational fluid dynamics models, ensuring that no matter the shape or size, the Reese's experience remains consistent. Every year, the production line adapts to create special seasonal versions of Reese's Peanut Butter Cups, which introduces another layer of complexity to the manufacturing process. For Halloween, pumpkin-shaped cups are crafted, while Christmas brings tree-shaped varieties and Easter features egg-shaped versions, all of which require entirely different molding systems. Instead of the standard fluted cup molds used year-round, these limited editions use custom-engineered molds with unique contours that must still ensure even chocolate distribution, stable cooling, and a clean release during demolding. These seasonal shapes often necessitate recalibrating the chocolate depositor systems and modifying the cooling tunnel timings, since broader or thicker designs may set at different rates than standard cups.